On the surface of Europa, there is no sound of waves breaking, no shoreline, and no sunlight reflecting from open water. There is only a sheet of ice so vast that it covers the entire world, divided by reddish-brown fractures stretching for hundreds of kilometers. In some places, bands of ice overlap like pieces of glass that were once shattered and then frozen back together. Elsewhere, the surface appears relatively smooth, yet beneath that cold outer shell, material seems to be moving very slowly. Hello and welcome to Night Cosmos Sleep. On this journey, we will spend some time beside one of the most mysterious worlds in the solar system, where an enormous ocean may have existed in darkness for billions of years without ever being seen by a camera. Europa is one of Jupiter's large moons. It is smaller than Earth's moon, but its surface is made almost entirely of water ice. Sunlight is far weaker there than it is on Earth, and temperatures are low enough for the moon's outer layers to remain frozen as a lasting shell. Seen from space, Europa appears as a pale white sphere, covered in long reddish-brown streaks, like veins running across a surface that seems completely still. Above the ice, there is no exposed ocean. There are no waves rolling toward the horizon, no rain clouds, and no rivers carrying water from one place to another. Any liquid water on Europa must lie deep below the surface, hidden beneath an ice shell that may be many kilometers thick. Yet scientists believe this concealed ocean could cover nearly the entire moon and contain roughly twice as much water as all of Earth's oceans combined. That number can be difficult to imagine when heard on its own. Gather the Pacific, Atlantic, Indian, Arctic, and Southern Oceans into a single body of water. Then imagine nearly twice that amount hidden beneath the icy shell of a moon smaller than our own. No light reaches the water's surface. There is no thick atmosphere above it to create wind. There is only water, rock, ice, and darkness extending across spans of time far greater than the whole of human history. So far, no spacecraft has drilled through Europa's ice to reach the ocean below. No camera has ever returned an image of its surface. What humanity has observed lies mostly above: fractures, colored bands, blocks of ice that were once displaced, and regions that appear younger than the terrain around them. These features suggest that Europa may not be a completely dead and motionless body of ice. Some of the moon's internal energy may come from the tidal forces of Jupiter. As Europa moves along its orbit, the immense gravity of its parent planet repeatedly stretches and gently compresses its interior. Over time, that motion may generate heat, helping to preserve a layer of liquid water beneath the ice. Even so, the surface can tell only part of the story. A fracture may reveal that the ice once experienced stress, but it cannot directly show how deep the ocean is. A disrupted region may suggest that material moved upward from below, but it cannot confirm the composition or salinity of the liquid layer. Cameras can observe the shape of the surface, while the ocean itself remains beyond sight. This is the fundamental difficulty of studying a world sealed beneath ice. Visible light reflects only from the outermost layer. It cannot travel through many kilometers of ice and return with a clear image of what lies below. Radar can probe deeper, but its signal is affected by the structure, temperature, purity, and fractures within the ice. The farther it travels, the weaker and more difficult to interpret it becomes. So how can we know that an ocean exists in a place where light can never reach? The answer begins not with water, but with something else that is completely invisible: a magnetic field. Jupiter produces the strongest planetary magnetic field in the solar system. It extends far into space and surrounds the moons moving through their orbits. Europa continually passes through this magnetic environment. Because Jupiter rotates rapidly and its magnetic axis is not perfectly aligned with its rotational axis, the strength and direction of the field experienced by Europa change over time. At the surface, these changes create no spectacle that the eye can see. The ice does not begin to glow. The fractures do not vibrate in a way a camera could record. But deep below, if a salty ocean exists, The changing magnetic field may cause electrically charged particles in the water to begin moving. Pure water does not conduct electricity well, but water containing dissolved salts is different. When salts dissolve, they separate into electrically charged ions. These ions can move through the liquid. As a changing magnetic field passes through the ocean, it can generate electrical currents that are extremely weak but spread across an enormous area. Those currents then produce a magnetic field of their own. The ocean, then, does not simply rest beneath the ice. It responds to Jupiter's magnetic environment. The secondary magnetic field created by the ocean passes back through the icy shell and blends with the field outside. As a result, the magnetic field around Europa is altered very slightly from the form it would have if the moon's interior contained only ice and rock. A spacecraft can measure this change from outside. Its instruments do not photograph the water, touch the ocean, or drill through the ice. They simply detect that the magnetic field has been distorted in a way consistent with the presence of a layer of electrically conductive material deep inside Europa. This is one of the most beautiful ideas in the study of icy worlds. An ocean hidden completely from view can still leave traces beyond itself. The ice may prevent light from passing through, but it cannot stop the ocean from responding to a changing magnetic field. Salt water does not need to reach the surface. The moment its ions begin to move, the ocean starts sending information out into space. Decades ago, the Galileo spacecraft flew past Europa and measured variations of this kind. Its data did not produce an image of the ocean, but it became some of the strongest evidence that a global layer of salty water may exist beneath the ice. A tiny signal within an invisible field allowed humanity to infer the presence of a body of water larger than all the oceans on Earth combined. However, making that measurement is far from simple. The space around Jupiter is filled with charged particles, plasma, and many other magnetic fluctuations. The spacecraft itself also produces magnetic interference from its electrical systems, wiring, and instruments. A sensor must be sensitive enough to detect Europa's faint signal, yet stable enough not to mistake changes within the instrument for genuine variations in space. This is where the story begins to shrink in scale. From an ocean surrounding an entire moon, we will move toward crystals only a few millimeters across. From induced electrical currents flowing through millions of cubic kilometers of water, we will descend to the states of electrons surrounding an atomic-scale defect in diamond or silicon carbide. The contrast seems almost impossible. At one end lies a planetary ocean beneath the ice. At the other is an extraordinarily small imperfection in a crystal structure. Between them is a magnetic field carrying information from a place that has never been seen to a tiny sensor drifting through space. Europa has not yet opened its icy shell to humanity. The ocean below remains in darkness, with no photographs, no water samples, and no instrument that has ever touched it directly. But that silence is not absolute. Each time Jupiter's magnetic field sweeps past, the ocean may be responding with a very faint signal, just strong enough to alter the space around the moon. To find an ocean that cannot be seen, we must first understand salty water can behave like an electrical circuit, the size of a world, and why its magnetic signature can pass through ice, that visible light. On Earth, most of what we call the ocean lies exposed beneath the atmosphere. Sunlight reaches the water's surface, wind creates waves, and clouds carry moisture across continents before returning it as rain. This image is so familiar that it is easy to assume liquid water can exist only in this way, on the outside of a planet, beneath a sky, and within a temperature range warm enough for ice to melt. But as humanity explores deeper into the solar system, it is becoming clear that an ocean does not need a shoreline, does not need contact with sunlight, and does not need to lie on the surface of a world. Some of the largest bodies of water beyond Earth may exist in places that appear from the outside to be nothing but ice. They are sealed in darkness, resting between a cold outer shell and deeper layers of rock below. Rather than receiving heat directly from the sun, They may be sustained by energy generated inside their moons, especially through the constant flexing caused by the gravity of the giant planets they orbit. Worlds like these are often called ocean worlds. The name does not mean their surfaces resemble Earth. Most may have no liquid water exposed at all. Their oceans are completely covered by ice, sometimes so thick that a future probe might have to travel through many kilometers of frozen material before reaching the water. Yet even while hidden, these oceans may occupy a significant portion of the entire world's volume and persist for immense spans of time. Europa is one of the most striking examples. This moon orbits Jupiter in less than 3.5 days, completing each revolution far more quickly than our moon travels around Earth. Every orbit carries Europa through an environment dominated by Jupiter's powerful gravity, radiation, and vast magnetic field. Gravity does more than hold the moon in its path. It also gently pulls Europa's interior in changing directions throughout its journey. Europa's orbit is not a perfect circle. The distance between the moon and Jupiter changes slightly as it moves. When Europa is closer, Jupiter's gravity is stronger. When it is farther away, the pull becomes weaker. This small difference causes Europa's interior to flex and compress continually. The movement is not large enough for the human eye to notice at the surface, but over millions of years, it can generate heat. This source of energy is known as tidal heating, and it is one of the main reasons water beneath the ice may remain partially liquid rather than freezing solid. Europa can be imagined as a sphere being squeezed very gently over and over in a slow rhythm. Each deformation is small, but the material inside must constantly adjust. Friction and movement produce energy, much as a metal rod becomes warmer when it is bent back and forth repeatedly. On Europa, this process unfolds across an entire moon, and the heat it creates may help separate the outer ice shell from the deeper rocky interior with an ocean of liquid water. According to current models, this ocean may surround all of Europa. It may not be an isolated pocket of water beneath a single fracture, but a continuous layer extending around the entire moon. The ice above acts like an enormous roof, while the ocean floor may come into contact with the rocky interior below. That contact is especially important because, on Earth, interactions between water and rock play a major role in many chemical processes that can provide energy for living environments. Although Europa is smaller than our moon, it may contain an enormous amount of water. NASA estimates that Europa's ocean could hold roughly twice as much water as all of Earth's oceans combined. This may seem surprising when comparing the sizes of the two worlds, but the difference lies in depth. Earth's oceans form a relatively thin layer around a large planet. On Europa, the water may extend tens of kilometers deep or more, creating a very thick liquid shell beneath the ice. A small world can therefore hold an immense volume of water. Europa's entire surface area is only slightly larger than the continent of Africa, yet beneath its ice may lie an ocean deeper than any trench on Earth. There is no sunlight there to support photosynthesis, no summer to warm the water's surface, and no atmosphere delivering oxygen from above. Any energy useful for the ocean's chemistry would have to arrive through other pathways, such as internal heat, reactions between water and rock, or substances transported downward from the ice. For this reason, saying that Europa contains water answers only a small part of a much larger question. Water is an effective solvent, allowing many substances to dissolve and react with one another. But the presence of water alone is not enough to prove that life exists in a place. An environment may contain water while lacking an energy source, essential elements, or suitable chemical conditions. Discovering an ocean is therefore not the same as discovering organisms. It only suggests that one important component of a potentially habitable environment may be present. Farther away, around Saturn, Enceladus offers another version of an ocean world. This moon is far smaller than Europa. Its diameter is only a little more than 500 kilometers, small enough that the entire moon could fit within a relatively modest region of many countries on Earth. Seen from space, Enceladus is bright white, covered in ice, and reflects most of the light that reaches it. but near the South Pole, its surface is not completely sealed. There, long fractures known as tiger stripes cross the terrain. From these cracks, water vapor, ice particles, and material from the interior erupt into space in broad plumes. Some of this material falls back onto the surface, while some escapes and helps form one of Saturn's rings. Because of these plumes, the ocean of Enceladus is not entirely isolated behind the ice. It is carrying some of its interior material outward into a region that spacecraft can reach. The Cassini spacecraft flew through these plumes many times. Instead of landing and drilling through the ice, it only needed to pass through the cloud of particles drifting in space. Cassini's instruments analyzed the material that struck the spacecraft or passed through its detectors, allowing scientists to study the composition of the ocean below indirectly. The data revealed that the plumes contain water vapor and tiny particles of ice. Within those particles were salts, an important sign that liquid water may have come into contact with rock before being forced toward the surface. Cassini also detected a variety of organic compounds, meaning carbon-containing molecules, that can participate in complex chemistry. Other findings, including extremely small silica particles and molecular hydrogen gas, suggest that interactions between warm water and rock may be taking place on the ocean floor. On Earth, similar reactions occur around hydrothermal vents on the seafloor. Water seeps into hot rock, reacts with minerals, and then returns to the ocean carrying heat and chemical compounds. Some ecosystems on Earth survive around places like these without depending directly on sunlight. Instead of light, they use chemical energy to sustain their food chains. This similarity makes Enceladus an especially compelling place to study. It appears to have liquid water, organic compounds, and a potential source of chemical energy. Even so, these findings do not prove that life exists there. Organic compounds can form through many processes that have nothing to do with living organisms. Hydrogen gas can also be produced entirely through geochemical reactions. What Cassini discovered suggests that the ocean of Enceladus has several intriguing conditions, but the question of life remains open. Europa and Enceladus are therefore like two sealed rooms closed in different ways. In the first room, vapor is escaping through a crack in the door. We can bring an instrument close, collect the vapor, and analyze what it carries. Enceladus is like that room. Its south polar plumes act as a natural opening, carrying samples from the ocean into space without requiring humans to break through the ice. The second room is almost completely sealed. There is no obvious stream of vapor to collect regularly, and no large, continuous flow of material escaping in an easily accessible way. Yet an electrical system is still operating inside the room. From outside, we can measure small changes in the electric or magnetic field and recognize that something is responding behind the wall. Europa is closer to this second image. Its ocean remains largely enclosed beneath the ice, but the salty water inside may interact with Jupiter's magnetic field and leave a signal that can be measured from space. This comparison does not mean that Europa is entirely incapable of releasing material. Some observations have suggested that water vapor may occasionally appear above the surface, but those signs are not consistent and have not provided a clear sampling pathway like the plumes of Enceladus. A spacecraft flying past Europa cannot simply rely on passing through a dense stream of material and analyzing the ocean below. It must use more indirect methods. The two moons also differ in the environments surrounding them. Europa lies deep within Jupiter's powerful magnetosphere, where its surface is constantly bombarded by high-energy particles. Radiation can alter the chemistry of the ice, breaking molecules apart and creating new substances. Some of this chemically transformed surface material may gradually be carried deeper through geological processes, although the rate and extent of that exchange are still not well understood. Enceladus occupies a different environment around Saturn and displays clearly concentrated geological activity near its south pole. Internal heat causes the fractures there to open and close with the tidal cycle, allowing water and vapor to escape. Rather than keeping everything behind a sealed shell of ice, Enceladus continually releases tiny fragments of its ocean into space. This allows a spacecraft to examine the composition of the water without traveling directly beneath the surface. Europa, by contrast, forces us to learn how to read subtler signs. Fractures and regions of chaotic terrain show that the ice shell has moved in the past. These geological features suggest that material below may have applied pressure, broken the ice, or caused blocks of the surface to shift. But images of the surface are not enough to determine the structure of the ocean with certainty. Its depth, thickness, salinity, and connection to the rocky interior must still be inferred from many different kinds of measurements. Radar can send radio waves into the ice and analyze the signals that return. Gravity measurements can reveal how mass is distributed inside the moon. Thermal imaging can search for warmer regions where near-surface activity may be taking place. Analysis of surface composition can identify substances that may have risen from below. Each method is like a small window looking into the same room, but no single window reveals the entire interior. Among the signals capable of passing through the ice, magnetism has a particular advantage. The ice blocks visible light and makes radar interpretation complicated, but it cannot prevent a conductive ocean from responding to a changing magnetic field outside. If the water contains enough salt and forms a sufficiently broad layer, the ocean can behave like a natural electrical circuit. As the magnetic field of the parent planet changes, electric charges in the water move and generate a secondary field. That signal can emerge without requiring a fracture, a plume of vapor, or a stream of material erupting from the surface. This makes Europa a very different problem from Enceladus. At Enceladus, part of the story is carried outward in the form of ice particles that Cassini could touch directly. At Europa, the story is written in the way the entire moon alters the magnetic environment around it. One world passes samples through a crack in the door. The other allows its hidden interior to gently disturb invisible magnetic field lines outside. Both remind us that water in the solar system does not exist only in warm and brightly lit places. It can lie beneath ice, kept liquid by gravity, friction, and internal heat. It can interact with rock in darkness, dissolve salts, and take part in chemical reactions that require no sunlight. Worlds that appear completely frozen from the outside may contain environments far more dynamic than their surfaces suggest. The existence of these oceans also changes the way we think about habitable regions. In the past, attention often focused on the distance between a planet and its star, where surface temperatures might allow liquid water to exist. Europa and Enceladus reveal another path. A world can lie far from the sun, receive little light, and have an intensely cold surface, while still maintaining liquid water inside through tidal energy. This does not diminish the importance of starlight or heat from a star. It simply expands the number of ways a stable environment might form. Instead of searching only for planets that resemble Earth, scientists are also interested in oceans buried beneath ice, where chemical conditions may persist for billions of years. In some cases, the ice above may even protect the ocean from intense radiation and changes in the external environment. Even so, the distance between a potentially habitable environment and one that actually contains living organisms remains enormous. Water, energy, and organic chemistry are important ingredients, but they do not guarantee that life will emerge. An ocean may possess many favorable conditions and still be completely sterile. It is also possible that processes we do not yet understand are unfolding in the darkness beneath the ice. Science cannot fill that uncertainty with hope alone. It requires measurements, samples, and evidence that can be tested. Enceladus has given humanity a rare advantage. Its ocean carries some of its own material into space, allowing Cassini to perform analyses without ever touching the surface. Europa is not so accommodating. Most of its ocean remains trapped behind an immense shell of ice, and whatever happens inside is revealed only through indirect signs. So as we leave Enceladus and return to Europa, the question is no longer simply where the water is. We already have many reasons to believe that a vast ocean exists beneath the surface. The more important question is how that ocean can send information outward when light cannot travel down, cameras cannot see through the ice, and there is no steady stream of samples for a spacecraft to collect. Europa has almost completely closed its door. Yet behind that door, salty water may still move, electric charges may still respond, and an invisible field may still carry traces of the ocean through the ice. To understand how a sealed world can send a signal into space, we need to look more closely at the limits of light and radar, then follow another path along which information can travel. When a spacecraft flies past Europa, the first thing it sees is still the surface. The best cameras can capture long bands of fractures, regions where the ice has shifted, and blocks of terrain that seem to have broken apart before freezing back into place. These images can reveal a moon that is not entirely motionless, a world whose outer shell has endured tension, compression, and quiet movement from below. But no matter how sharp the images become, a camera can still see only the outermost layer of that world. Sunlight reaches the icy surface and reflects back toward the instrument. From that signal, scientists can distinguish color, brightness, shape, and terrain structure. They can measure the length of a fracture, identify a region of ice that appears younger than its surroundings, or recognize places where sections of the surface once shifted. These details are important because they show that the ice has passed through a complex history, yet they do not directly reveal what lies deep beneath it. A long fracture does not show how far below the surface the ocean begins. A region of chaotic ice does not reveal exactly how salty the water underneath may be. Nor can a patch of young terrain tell us on its own how thick the liquid layer is or whether it touches rock at the bottom. Images may suggest that Europa's interior remains active, but they cannot reconstruct the full structure of an ocean buried beneath many kilometers of ice. It is like standing outside a house and studying the wall. A crack in the paint may suggest that the foundation has shifted. A damp patch may hint at a leaking pipe inside. A fogged window may reveal that the temperature in the room differs from the air outside. But from those clues alone, we still cannot know the exact size of the room, how the plumbing is arranged, or what is happening in the deepest part of the house. Europa offers similar signs at its surface. The reddish-brown fractures did not appear at random. Some bands may have formed when the ice was pulled apart and material from below rose to fill the gap. Regions of chaotic terrain, where blocks of ice appear to have rotated, slid, or changed position, suggest that the shell is not a single completely rigid sheet. There may once have been pockets of water beneath it, warmer regions of ice, or movement from a deeper ocean that deformed the surface. Images like these make Europa look like a world with a geologically active past. But there is still a wide gap between seeing the evidence and understanding its cause. The same surface feature can sometimes be explained by several different models. A disrupted region may be connected to liquid water, but it could also have formed because of softer ice, trapped salts, or stress building within the shell. To discover what truly lies below, humanity needs a method that can reach deeper than visible light. Radar is one of the most natural tools for this task. Instead of collecting only the light reflected from the surface, radar sends radio waves down into the ice and listens for the signals that return. When those waves encounter a boundary between two different materials, some of their energy may be reflected. From the time it takes the signal to return and the ways it changes, scientists can infer that another layer of material lies below. On Earth, ice-penetrating radar has helped map the ice sheets of Greenland and Antarctica, locate lakes buried deep below the surface, and measure the thickness of glaciers. The same basic idea can be applied to Europa. A sufficiently powerful radar signal may travel down through the icy crust, reflect from internal boundaries, and return to the spacecraft. Under favorable conditions, the instrument may detect different layers of ice, pockets of liquid material, or perhaps even the boundary between the shell and the ocean beneath it. But Europa's ice is not necessarily a clear and uniform block of material. It may contain salts, dust, compounds altered by radiation, regions with different crystal sizes, and countless fractures. Temperature may also change with depth. Near the surface, the ice is extremely cold and rigid. Farther down, internal heat may make it warmer, softer, and more responsive to radar waves in different ways. Each of these changes can weaken, scatter, or redirect the signal. Instead of returning as a clean echo, the radar wave may come back as a complicated mixture of overlapping reflections. A small fracture, a pocket of salt, or a region of deformed ice can all produce signals that make interpretation difficult. Radar can be imagined as calling into a cave and listening for the echo. In a cave with smooth walls, the sound returns fairly clearly, and the delay between the call and the echo can reveal the distance. But when the cave contains many chambers, rough surfaces, and branching passages, the sound reflects in many directions. Some echoes return early, some arrive later, and others become so weak that they nearly disappear. A person standing outside can tell that there is structure within, but reconstructing its exact shape from those echoes is far from simple. Radar at Europa faces a similar problem, except that it uses radio waves instead of sound. If the ice is relatively pure and favorably structured, the signal may travel deep. If the ice contains many conductive impurities or too many scattering regions, the waves may be absorbed before they ever reach the ocean. The depth radar can probe, therefore, depends not only on the power of the instrument, but also on the nature of the ice itself. None of this makes radar less valuable. On the contrary, it remains one of the most important tools for studying Europa's near-surface structure. But like a camera, radar cannot answer every question on its own. It may reveal layers, boundaries, and unusual regions, yet turning those signals into a complete picture of the ocean's thickness, depth, and composition still requires many other kinds of measurements. Visible light and radar both depend on sending or receiving a form of electromagnetic wave, and then studying how that wave interacts with matter. Visible light is blocked almost immediately at the surface. Radar can travel farther, but it is still strongly affected by the structure and composition of the ice. For this reason, scientists also search for another kind of signal, one that does not need to create a direct image of the ocean but can still carry information about what lies beneath. A magnetic field provides such a path. This does not mean that magnetic fields pass through all matter without being altered in any way. More precisely, ice does not shield against a magnetic field in the same way it blocks visible light. A magnetic field can extend through the ice, interact with a conductive layer of liquid below, and then appear outside again as a measurable change. If light is like someone standing outside a house who can see only the wall, then a magnetic field is like a gentle vibration passing through that wall. The vibration reaches something inside, causes it to respond, and returns in an altered form. The observer cannot see the room, but from the change in the signal, they can infer that a structure inside is responding. On Europa, that responding structure may be a salty ocean. As Jupiter's magnetic field changes around the moon, electric charges in the water move and generate currents. Those currents, in turn, produce a magnetic field of their own. This secondary field blends with Jupiter's field, causing the magnetic environment around Europa to change in a subtle but predictable way. A spacecraft measuring that variation does not need to see through the ice. It only needs to pass through the right region of space with a sensor sensitive enough to detect it. From the shape, strength, and timing of the signal, scientists can construct models of the conductive layer inside. They can ask whether that layer is broad enough to be a global ocean, how deeply it lies, and whether its electrical conductivity is consistent with salty water. Even so, a magnetometer is not a machine that instantly produces a complete map. It does not return images of waves, the seafloor, or the ice shell. It measures an invisible field and leaves scientists to draw conclusions from the data. Many other factors can also affect the magnetic environment, from the plasma surrounding Jupiter to interference created by the spacecraft itself. The case for an ocean becomes strongest only when magnetic measurements are compared with surface images, radar data, gravity measurements, and geological models. Each instrument therefore observes Europa in a different way. Cameras reveal the moon's outer skin. Radar tries to listen for echoes from within the layers of ice. Magnetometers measure how the interior responds to Jupiter's magnetic environment. No single method can fully open the shell, but together they can gradually narrow the range of possibilities. Even as orbital observation technology continues to improve, the idea of traveling directly down to the ocean remains deeply compelling. A future lander might carry drilling equipment or a probe that uses heat to melt slowly through the ice. Such a device is often imagined as a narrow, heavy machine capable of pulling itself downward by warming the ice ahead of it and allowing the water to freeze again behind it. In theory, a melting probe could carry chemical sensors, cameras, and a communication system. After a long descent, it might reach liquid water and release a smaller instrument into the ocean. Humanity would no longer be limited to making inferences from outside, but could directly measure temperature, salinity, chemical composition, and the particles drifting through the water. But the distance between that idea and a real mission is enormous. The first challenge is energy. Melting through many kilometers of ice would require a steady source of heat over a long period. Europa lies far from the sun, so solar power is limited, while nuclear systems would need to be designed with exceptional safety and durability. The probe would have to operate in extreme cold, survive radiation before beginning its descent, and continue transmitting data while buried deep beneath the ice. Communication presents another challenge. Radio waves do not pass easily through a thick ice shell with a complex composition. A descending probe might need to trail a cable behind it or leave small relay stations along the way. Every additional component would make the system heavier, more complicated, and more vulnerable to failure. There is also the danger of contamination. A machine built on Earth could carry bacteria, spores, or organic molecules from our own environment. Even with extremely careful sterilization, guaranteeing that no form of life survives the journey would be extraordinarily difficult. If the mission's goal were to search for biological signs in an extraterrestrial ocean, accidentally carrying Earth material into it could distort the results or alter an environment that had never encountered anything from our world. This issue is not only scientific, but also a matter of responsibility. An ocean that has remained isolated beneath ice for billions of years, especially if it possesses its own distinct chemical environment, must be approached with great care. Humanity cannot simply drill downward out of curiosity without considering the possibility of contaminating the very place it hopes to study. For that reason, scientists need to know a great deal before sending a machine through the ice. How thick is the shell at the intended landing site? Are there regions where it is thinner or younger? Is there a continuous ocean below, or only isolated pockets of water? Does the ice contain enough impurities to trap the probe? Are there locations close enough to geological activity to shorten the descent while still remaining stable enough for a landing? Most of these questions must be answered from orbit or during close flybys. Cameras identify the terrain and relatively safe regions. Radar searches for structures within the ice. Thermal measurements look for areas that may be warmer. Magnetometers help confirm the presence and broad characteristics of the conductive liquid layer lying far below. A mission that drills through the ice would therefore not be the first step, but perhaps the result of decades of indirect observation. Before opening the door, humanity must know how thick it is, what may lie behind it, and where the best place to enter might be. This is also why magnetic measurements are so important. They do not require the ice to be transparent. They do not depend on a fracture actively releasing material into space. They require only that the ocean conduct electricity and that the external magnetic environment change enough to create a measurable response. Light shows us what the surface has endured. Radar attempts to explore the layers of ice covering the ocean. But magnetism allows us to ask a different question. How does Europa's interior respond when Jupiter's magnetic field sweeps across it? That question does not produce an image in the usual sense. It produces a trace, a slight distortion in an invisible field. Yet from that trace, humanity can infer that beyond the ice there is more than cold, silent rock. We cannot yet see through Europa's entire outer shell. We cannot lower a camera into its ocean or collect water from many kilometers below the surface. But a salty ocean is not completely isolated from the surrounding space. As Jupiter's magnetic field changes, the ocean may respond, generating electrical currents and sending traces of its presence back outward. To understand that signal more clearly, we need to move beyond the images captured by cameras and the echoes returned by radar, and begin to see Europa as a natural electrical circuit the size of a world, where salt water, ions, and magnetic fields combine to create a quiet response beneath the ice. An ocean can become an electrical circuit without wires, batteries, or any artificial equipment. On Europa, this may happen in complete darkness beneath a thick shell of ice, where salty water responds to Jupiter's immense magnetic field. The ocean emits no light and sends no waves to the surface, yet the charged particles within it can still move. It is this quiet motion that allows a hidden body of water to leave a trace in the space beyond. To understand how this works, we first need to look more closely at salt water. A cup of nearly pure water does not conduct electricity, as well as many people assume. Water molecules can interact with an electric field, but when very few freely moving charged particles are present, electric current cannot pass through the water easily. When salt dissolves, its crystal structure separates into ions. Some carry positive charges, while others carry negative charges, and all of them can move through the liquid. In Earth's oceans, salt does more than create a salty taste. It also allows seawater to conduct electricity more effectively than pure water. Sodium ions, chloride ions, and many others drift among the water molecules, constantly colliding and changing direction. Under ordinary conditions, their motion is largely random. But when the electric or magnetic environment around the ocean changes, some of that motion can become more organized, forming an electric current. Europa's subsurface ocean may contain salts and dissolved minerals released through long-term interactions between water and rock. We do not yet have a water sample that would allow us to measure its salinity directly, so its exact composition remains unknown. Even so, models of Europa's interior, substances observed on its surface, and especially the Moon's magnetic response are all consistent with the presence of a conductive liquid layer beneath the ice. The force acting on that layer of water comes from Jupiter. This giant planet rotates extremely quickly, completing one turn in less than 10 hours. Within Jupiter, flows of electrically conductive material generate a powerful magnetic field that extends far into the surrounding space. This field not only surrounds the planet, but also reaches the orbits of many of its moons, including Europa. If Jupiter's magnetic field were perfectly uniform and unchanging at Europa's location, the ocean would not produce the same kind of response scientists are searching for. The key is variation. Jupiter's magnetic axis is not perfectly aligned with the planet's rotational axis. As Jupiter spins, the structure of its magnetic field moves with it, causing the strength and direction of the field experienced by Europa to change in a relatively regular rhythm. We can imagine Europa resting within an invisible current that is constantly changing direction. Each time Jupiter rotates, the magnetic environment around the Moon grows stronger, becomes weaker, or tilts in a different direction. The ice above does not respond in a way that produces large electrical currents, but the salty ocean below may. The ions in the water sense the changing field and begin to shift in an extremely subtle collective motion. No enormous current of water suddenly swirls around Europa. The ions do not race from one side of the Moon to the other. The movement is far more delicate. The changing magnetic field creates an induced electric field, which encourages charged particles in the ocean to move in vast loops of electric current. These loops may extend across the entire layer of water, forming a circuit without wires, created by the ocean itself. This phenomenon is known as electromagnetic induction. The term may sound technical, but the underlying idea is quite familiar. A changing magnetic field can generate an electric current within a conductive material. That newly formed current then creates a magnetic field of its own. The process does not require two objects to touch, nor does it require a power source to be connected directly to the conductive layer. An induction cooktop offers a familiar example, though it should be understood only as a small-scale image that helps make the idea easier to picture. Beneath the cooktop's glass surface is a coil carrying a changing electric current. This current creates a rapidly varying magnetic field. When a suitable pot is placed above it, the field induces electrical currents within the metal. The metal's electrical resistance converts the energy of those currents into heat, warming the pot without the use of a flame. On Europa, there is no coil, no cooktop, and no pot. The changing magnetic field comes from Jupiter, while the conductive material is the salty ocean. The purpose of the process is not to generate heat for cooking. The similarity lies only in the principle. A varying magnetic field can cause electric charges to move through a conductive material without a direct wire connecting the source to that material. Wireless charging works through a closely related idea. A coil in the charging base creates a changing magnetic field, which induces an electric current in another coil inside the device. Energy crosses a small gap without a metal plug, making direct contact. At Europa, there is no second device designed to receive that energy. Yet the conductive ocean still responds to the changing magnetic field, and that response produces a new signal. That new signal is the magnetic field generated by the electric currents within the ocean. Every electric current is accompanied by a magnetic field. As ions in the salty water move in broad current loops, they create a secondary field surrounding Europa. This field is far weaker than Jupiter's magnetic field, but it is not completely hidden. It overlaps with the original field and causes the overall shape of the magnetic environment around the Moon to shift slightly. It is like adding a small ripple to a powerful current. The main flow still dominates, but the shape of the water is no longer exactly the same as before. An observer close enough, with instruments precise enough, could detect that another motion is contributing to the whole. Around Europa, Jupiter's magnetic field is the great current, while the ocean's response is the small ripple added to it. Another image may help make this clearer. Imagine a sealed bowl containing water, with a hand stirring it very gently from within. We cannot see the hand, and we cannot see the surface of the water, because the bowl is covered. Yet the motion inside may reach the walls of the bowl as faint vibrations. By measuring at the right frequency and at the right moment, someone outside could recognize that the interior is not completely still. On Europa, the ocean does not literally make the ice vibrate in the way this image suggests. What travels outward is a change in the magnetic field. Jupiter creates the original rhythm, the ocean responds, and the secondary magnetic field carries that response through the ice. A spacecraft passing close to the Moon can measure the difference between Jupiter's expected magnetic field and the field that actually exists around Europa. The timing of the response is just as important as its strength. The ocean does not simply produce a magnetic field that is arbitrarily strong or weak. Its response must be connected to the rhythm of Jupiter's changing magnetic field. As the external field shifts in direction or intensity, the electrical currents in the ocean change with it. The secondary magnetic field appears with a particular strength and delay, depending on the conductivity, depth, and structure of the liquid layer. Scientists are therefore not searching for a single number on an instrument. They track how the signal changes over time, compare its direction with Jupiter's magnetic field, and determine whether the response repeats according to the expected rhythm. A signal that appears randomly is more difficult to explain. A signal that changes regularly in step with the external magnetic environment suggests that a conductive layer inside the moon is responding. The ocean's electrical conductivity affects the strength of that response. Water containing many ions generally allows stronger induced currents than nearly pure water. A broad, continuous liquid layer also responds differently from small, isolated pockets of water. The induced magnetic field may therefore carry information not only about the presence of liquid, but also indirectly about the conductivity and scale of that layer. Even so, a magnetic signal cannot immediately provide an exact measurement of salinity. Several different conditions can produce similar responses. A deep ocean with moderate conductivity may sometimes create a signal resembling that of a shallower layer containing more ions. The thickness of the ice shell, the location of the ocean, and the structure of the rocky interior also influence how the data are interpreted. This is why scientists construct many different models and compare them with the full range of measurements. They ask not only whether the signal is consistent with salty water, but also which model can simultaneously explain Europa's surface features, orbital motion, gravitational field, and magnetic response. An explanation that fits one measurement but conflicts with the others is not convincing enough. An important limit must also be kept in mind. Not every magnetic distortion around a celestial body proves that an ocean exists inside it. Plasma, charged particles in the magnetosphere, and electrical currents flowing through the surrounding space can also affect the measurements. In theory, rock or other conductive materials within a moon could produce a response as well. The case for Europa's ocean becomes compelling because many separate lines of evidence point toward a similar internal structure. The moon's surface consists mainly of water ice. Its fractures and regions of chaotic terrain show that the shell has moved in the past. Its density and orbital characteristics are consistent with a world composed of different internal layers. Most importantly, the strength and rhythm of the magnetic signal are consistent with a conductive liquid layer beneath the ice. In this context, salty water is a more natural explanation than a layer of metal or some unusual conductive material near the surface. Europa formed in the cold outer region of the solar system, where water ice is abundant. Tidal heating could maintain liquid water inside, while contact between water and rock could supply the ions that make the ocean conductive. No single piece of evidence is decisive on its own, but together they form a coherent picture. NASA sometimes describes oceans like this as planetary-scale electrical circuits. This does not mean that Europa contains a network of wires like the devices we use on Earth. It emphasizes that the entire layer of salty water may take part in a vast electromagnetic process. The changing magnetic field of the parent planet provides the external influence. Ions in the ocean form electrical currents, and the secondary magnetic field becomes the responding signal. The scale of this process is what makes it remarkable. In a laboratory, a researcher can create electromagnetic induction in a coil only a few centimeters wide. On Europa, the conductive circuit may extend around an entire moon. The current may be extremely weak in any individual region of water, yet the combined response of a global ocean can be large enough to alter the magnetic field in the surrounding space. This process continues as Europa moves through Jupiter's magnetic field. There is no single moment when the ocean switches on. The external field changes, the induced currents rise or fall, and the secondary magnetic field changes with them. Europa is like an enormous musical instrument driven by an invisible rhythm, while the ocean below responds with a sound that only a magnetometer can hear. The comparison with sound helps illustrate the relationship between the external influence and the response. When a glass is struck, its shape and material determine the sound it produces. An empty glass resonates differently from one filled with water. In the same way, Europa's magnetic response depends on its internal structure. A moon made only of ice and rock would respond differently from one containing a vast conductive ocean. The spacecraft does not need to hear an actual sound. It measures the direction and strength of the magnetic field at each moment during a flyby. Scientists then remove the portion of the signal expected from Jupiter examine the effects of the surrounding plasma, and search for what remains that may have been generated inside Europa. The work is like trying to identify a quiet instrument within a large orchestra, where every source is changing over time. The spacecraft itself can also interfere with the measurement. Electrical currents flowing through wires, engines, computers, and other systems all create small magnetic fields. For this reason, magnetometers are often mounted on a long boom extending away from the spacecraft, placing the sensor farther from sources of electromagnetic interference. Even then, engineers must characterize the magnetic behavior of every onboard system and calibrate the data with great care. When a spacecraft passes Europa only briefly, the opportunity to collect data is limited. The closest approach distance, the direction of the flight path, the state of Jupiter's magnetosphere, and Europa's position within the magnetic cycle all affect the quality of the measurements. A single flyby may provide a powerful clue, but repeated encounters under different conditions make it easier to separate the ocean's signal from external fluctuations. From a physical perspective, the idea of a conductive ocean responding to a magnetic field is relatively clear. Water containing ions allows electric charges to move. A changing magnetic field generates induced currents. Those currents create a secondary magnetic field. The secondary field makes the magnetic environment around the Moon different from what it would be if the interior contained only ice and rock. But a plausible mechanism is not yet observational evidence. An instrument must travel to the right place, measure at the right moment, and record the magnetic distortion with sufficient precision. The data must then be compared with many different models to determine whether a salty ocean truly provides the best explanation. For many years, Europa offered only clues through its fractured surface and theoretical models. Then a spacecraft entered the Jupiter system, carrying a magnetometer designed to measure the invisible fields surrounding planets and moons. As Galileo passed close to Europa, the idea of a planetary-scale electrical circuit finally had an opportunity to be tested in space. The spacecraft did not see through the ice. It did not touch the water or return with a sample of the ocean. But within the magnetic data recorded during its flybys, Galileo detected a response that the outer ice shell alone would have struggled to produce. From that moment on, the ocean beneath Europa was no longer merely a possibility suggested by fractures on the surface. It had begun to leave a measurable trace in space. When Galileo entered orbit around Jupiter in late 1995, the spacecraft had not come merely to observe a single planet. Before it lay an entire vast system of faint rings, turbulent plasma, and many moons with very different geological histories. Among them, Europa was only a relatively small sphere of ice, pale and nearly silent. There were no enormous plumes erupting clearly enough to guide the spacecraft. There was no thick atmosphere or moving cloud cover to reveal activity within. Every important clue lay in the very small changes Galileo could record as it flew past. Galileo studied the Jupiter system until 2003. During that time, it made 12 close approaches to Europa, each encounter offering a different view of the Moon. On some passes, its cameras photographed long fracture bands and regions of chaotic terrain. On others, instruments measuring charged particles examined the plasma environment near the surface. The spacecraft's magnetometer tracked how Jupiter's magnetic field changed as Galileo entered and then moved away from the space surrounding Europa. No single flyby lasted long enough for the spacecraft to observe the entire Moon continuously. Galileo had only brief intervals when Europa grew larger before its instruments swept past at close range and then quickly receded behind it. Each encounter was like a thin slice through an immense environment. From these separate slices, scientists had to reconstruct a three-dimensional picture of an invisible field that was constantly changing. Galileo's cameras could see the ice, but they could not see through it. The images revealed that Europa's surface appeared younger than those of many other moons. It had relatively few large impact craters, suggesting that the outer shell had been renewed in the relatively recent geological past. Long bands crossing the ice showed that the crust had once been stretched, fractured, and then filled with new material. In some regions, blocks of ice appeared to have broken away from their original positions, rotated slightly, and frozen again within a chaotic background. These images made the idea of a subsurface layer of water more plausible, but they were still not enough to confirm a global ocean. Warm, soft ice can move even without an ocean extending around the entire moon. Local pockets of liquid might form near the surface and later freeze. A slowly convecting ice shell could also create some of the structures seen by the cameras. To move beyond geological clues, Galileo needed another way to sense Europa's interior. The magnetometer provided that path. The instrument did not create an image, nor did it transmit a signal toward the surface. It measured the strength and direction of the magnetic field at the spacecraft's location. At each moment, the sensor recorded a vector, a value describing how strong the field was and which way it was pointing. By combining thousands of consecutive measurements, scientists could see how the magnetic field changed along Galileo's flight path. But those numbers did not tell the story on their own. Most of the magnetic field around Europa came from Jupiter, a powerful, complex, and constantly changing source. To identify the moon's own influence, scientists first had to know the spacecraft's position with great precision. Even a small error in position or timing could alter the background magnetic field predicted by the model. Galileo's trajectory, therefore, had to be reconstructed carefully from communication data, velocity measurements, and the gravitational motion of the spacecraft. During every Europa flyby, the research team needed to know the distance of closest approach, the direction of travel, the spacecraft's position relative to Jupiter, and the state of the magnetic environment at that moment. A magnetic measurement became meaningful only when it was placed correctly in both space and time. Then came the challenge of modeling Jupiter's background magnetic field. The planet's field is far stronger than Earth's, and its magnetic axis is tilted relative to its rotational axis. As Jupiter spins, the direction and strength of the field at Europa change in a repeating rhythm. In addition, the space around the planet is filled with plasma, charged particles, and large electrical currents that can alter the magnetic field in ways that are difficult to predict completely. Scientists could not simply examine a section of data and declare that the difference must come from an ocean. They had to construct a model of what Galileo should have measured if Europa produced no significant magnetic response. That model included Jupiter's main field, the spacecraft's position, the planet's rotation, and the influence of the surrounding environment. Only when the actual data were compared with the predicted curve did the difference begin to emerge. During Galileo's close passes by Europa, the magnetometer recorded a field that did not perfectly match the shape expected from the background model. An additional component caused the field's direction and strength to shift. The deviation was not large compared with Jupiter's magnetic field, but it appeared in an organized pattern. More importantly, the direction of this added component matched what a conductive layer inside Europa would produce while responding to a changing external field. The ocean would not create a fixed magnetic field like a bar magnet buried beneath the ice. What Galileo detected was closer to an induced field. As Jupiter's magnetic field changed, electrical currents arose within a conductive layer inside Europa. Those currents generated a secondary magnetic field that tended to oppose the original change. Europa's response was therefore closely connected to the rhythm of Jupiter's varying field. This was what made the data so significant. An intrinsic permanent magnetic field would maintain a relatively stable direction based on the moon's internal structure. An induced field, by contrast, changes with the external field that drives it. When Galileo encountered Europa, at different points in Jupiter's magnetic cycle, the measured response changed as well. That dependence was consistent with a conductive layer responding to the magnetic field of its parent planet. Even so, the conclusion did not emerge immediately after the first measurement. An unusual signal could come from many sources. Plasma around Europa could generate electrical currents. Charged particles striking the surface could create an extremely thin atmosphere and produce electromagnetic effects. The spacecraft itself carried many electrical systems capable of introducing interference. Each possibility had to be examined before the remaining signal could be attributed to a structure deep inside the moon. Engineers mounted the magnetometer on a boom extending away from Galileo's main body to reduce the influence of the spacecraft's electrical equipment. Even so, the data still had to be calibrated according to the spacecraft's operating state and known sources of interference. A small change in onboard electrical current could create a signal near the sensor. For that reason, research teams compared the magnetometer readings not only with environmental measurements, but also with the spacecraft's operational records. The effects of plasma also had to be considered. Europa moves through a region filled with charged particles trapped by Jupiter's magnetic field. When this plasma encounters the moon, its flow is slowed, redirected, and forced to interact with the extremely thin layer of gas surrounding the surface. These processes can distort the magnetic field even without an ocean. To separate these two influences, scientists had to examine the spatial shape of the signal. A response produced by plasma is usually concentrated in particular regions around the moon and depends on the flow of charged particles. An internally induced field, by contrast, has a shape more like that of a magnetic dipole generated within Europa. Galileo's flight paths cross different regions, allowing the research team to compare the data with models of both kinds of response. No simple model could reproduce every detail perfectly. The environment around Jupiter is too complex for all uncertainty to be removed. But even after the plasma-related effects were taken into account, an induced field within Europa remained the best explanation for the most important part of the signal. The strength and direction of this field suggested that the conductive layer was not confined to a small region, but could extend around much of the moon. At this point, Europa's composition became an essential piece of the evidence. An induced signal tells us only that conductive material exists inside. In principle, that material does not have to be water. A layer of molten metal or some other conductive substance could also generate electrical currents as the magnetic field changes. But Europa is a world rich in water ice, with a density and internal structure that do not support the presence of a broad metallic layer near the surface. Tidal heating could keep some of the water beneath the ice in a liquid state, while dissolved salts and minerals would make that water electrically conductive. When all these factors are considered together, a salty ocean becomes the most reasonable explanation. Images show that the ice shell has moved in the past. Thermal models suggest that the interior may be warm enough to sustain liquid water. The moon's mass distribution is consistent with a thick layer of water, and the magnetometer detected the kind of response that a vast layer of conductive liquid would be expected to produce. No single piece of evidence completes the story on its own. The cameras did not see the ocean. The magnetometer did not directly measure its salinity. Thermal models cannot determine its exact depth, but when several independent forms of data all point toward a similar structure, the case for an ocean becomes far stronger than any individual clue could make it. The process can be imagined as reconstructing a locked room from traces found outside. A damp mark on the wall suggests that water may be present within. A steady sound hints that machinery is still running. An electricity bill shows that energy is being used. None of these clues allows anyone to see directly into the room, but when they all support the same explanation, the picture of what lies inside gradually becomes clearer. At Europa, the slight distortion in the magnetic field plays a role similar to a sound coming from behind the door. It does not reveal what the ocean looks like, but it shows that a very large conductive layer is responding to Jupiter. The induced magnetic field became one of the strongest pieces of evidence because it is directly connected to a physical property of salty water, the ability of ions to move and create electrical currents. The different flybys also helped determine whether the signal repeated. Galileo did not encounter Europa under the same magnetic conditions each time. Jupiter had rotated to a different orientation. The field acting on the moon had changed in strength and direction, and the surrounding plasma environment had shifted as well. This created a natural experiment. If Europa contained a conductive layer, its response should change with the external field rather than remain fixed. When data from different times were compared, the induction model continued to fit. The secondary field did not appear as an independent source, but responded to Jupiter's field in a predictable way. It was this consistency across changing conditions that made the ocean explanation more convincing. Even so, Galileo's data could not answer every question precisely. The depth of the ocean still depended on models of the ice shell and electrical conductivity. Its salinity could fall within a wide range. Warm layers of ice or pockets of water near the surface might make the internal structure more complicated. The magnetic response provided a broad view of the conductive layer, but not a detailed map like a photograph. A thick ocean with relatively low salinity can sometimes produce a signal similar to that of a thinner ocean with greater conductivity. This creates a trade-off within the models. To separate those possibilities, scientists need additional data from radar, gravity measurements, high-resolution imaging, and flybys arranged under a wider range of magnetic conditions. Galileo therefore did not close the question of Europa. It changed the nature of the question. Before those measurements, scientists were mainly asking whether the fractures on the surface could be explained by liquid water. Afterward, they had stronger reasons to ask how deep the ocean was, how much salt it contained, how it interacted with the rock below, and how material might move between the ocean and the surface. That shift happened without a single dramatic moment. No image appeared on a screen showing a dark sea beneath the ice. No solitary signal sounded out and announced that an ocean had been found. Instead, there were long sequences of numbers, curves drawn and redrawn, models revised, and comparisons that continued over many years. As Galileo flew past Europa, the moon retained its silent appearance. The icy surface did not open, the ocean did not glow. The magnetometer recorded only a slight deviation in the direction of an invisible field. But when that deviation was placed along the spacecraft's precise trajectory, compared with Jupiter's background field, and considered alongside what the cameras had seen on the surface, a vast ocean began to emerge within scientific models. This is one of the ways science often moves forward. Great discoveries do not always arrive as an object seen for the first time. Sometimes, they appear as what remains after every known influence has been carefully removed. A small signal persists, repeats, and agrees with a physical mechanism. From that signal, a structure that cannot be observed directly, gradually, becomes difficult to deny. Galileo showed that a magnetometer could do more than map the magnetic field of a planet. It could become a tool for probing the interior of a world. Instead of penetrating the ice with a drill, the instrument used Jupiter's own magnetic field as a natural source of stimulation. The ocean responded, and the spacecraft measured that response from outside. This idea opened another way to search for oceans elsewhere in the solar system. A moon does not need to spray water into space, nor does its ice need to be transparent enough for radar to see all the way to the bottom. As long as a conductive liquid layer exists, and the changing magnetic field is strong enough, the structure inside can leave a trace around the world. But this approach also requires instruments of exceptional stability. The ocean's signal is usually far weaker than the magnetic field of its parent planet. It is mixed with interference from plasma, the spacecraft itself, and variations unfolding over time. Even during a mission lasting only a few years, tiny errors must be controlled with great care. On journeys lasting decades to more distant worlds, the demands become even more severe. Galileo was a large spacecraft carrying many instruments and designed for a complex mission around Jupiter. Future missions may not always be able to operate on the same scale. A small spacecraft, a secondary satellite, or a platform closer in size to a CubeSat has very little room, mass, and power available for sensors. A magnetometer must still be sensitive enough while also becoming lighter, consuming less energy, and surviving radiation for long periods. Stability also becomes a major concern. A sensor may perform well when it first leaves Earth, yet gradually drift over many years because of temperature changes, radiation, or the aging of its components. By the time the spacecraft finally reaches its destination, a very small error could be mistaken for a signal from an ocean. The ability to test or recalibrate itself may therefore become nearly as valuable as its original sensitivity. These requirements carry the story away from the scale of Jupiter and Europa and shrink it down into the interior of matter. Instead of relying entirely on traditional magnetic sensors, researchers began asking whether the quantum states of electrons inside a crystal could create a magnetometer that was smaller and more stable. Galileo proved that an ocean could leave a trace in a magnetic field. The next step is to build instruments small enough to travel farther, efficient enough to operate aboard compact spacecraft, and durable enough to listen for a faint signal after many years drifting through space. Then the tool used to search for oceans would no longer have to be only a sensor mounted on a long boom extending from a large spacecraft. It could begin with a tiny defect buried deep inside a crystal. The following is a midpoint anchor for the video, reducing the density of information and slowing the visual rhythm so the listener can reorient to the entire mechanism before the story descends into the world of crystals. For a moment, let us step away from the models, the data curves, and Galileo's flybys, and return to a simpler image. There is no need to picture all of Jupiter, follow Europa through its entire orbit, or think yet about the tiny quantum instruments that will appear later. We only need to follow the journey of a single magnetic field line as it approaches this icy moon. That field line is not a physical thread stretched through space. It is simply a way of visualizing the direction and shape of an invisible field. But in our imagination, we can picture it as a narrow path beginning in the immense region around Jupiter, where the planet's magnetic field reaches far beyond the clouds visible to the human eye. Jupiter continues to rotate rapidly, and its magnetic field changes with that rotation. The field line moves through space, crossing a region filled with plasma and charged particles before drawing closer to Europa. Ahead lies a pale sphere, covered entirely in ice and divided by long reddish-brown fractures. Nothing on the surface reveals that an invisible signal is approaching. The ice does not open. The fractures do not glow. The magnetic field line simply continues inward, extending through the cold shell in a way visible light cannot. It does not drill a passage or push the ice aside. The magnetic field is simply present within that material, continuing deeper below. Beneath many kilometers of ice, it encounters a different environment. There may be a salty ocean surrounding nearly all of Europa. There is no sunlight, wind, or familiar kind of wave found on Earth. There is only water, dissolved salt, and countless charged ions moving randomly among the molecules. As the external magnetic field changes, the electromagnetic environment within the ocean changes as well. The ions no longer drift only through random motion. A very small part of their movement begins to align, forming vast but faint induced electrical currents. There are no wires encircling the moon, but the salty water itself acts as the conductive material. That current spreads through the ocean. It produces no light and creates no sound that could travel upward to the icy surface. Yet every electric current generates a magnetic field. From the tiny movements of the ions, a secondary magnetic field begins to form inside Europa. The new field does not exist separately from Jupiter's magnetic field. It overlaps with the original field, bending some field lines slightly, strengthening them in one place and weakening them in another. The change is far too small to be seen, yet it still carries information about the liquid layer that created it. The secondary magnetic field continues outward. It passes back through the ice, returns to the space surrounding Europa, and merges with Jupiter's vast magnetic environment. The surface remains silent. the ocean remains concealed, but its trace has crossed the cold shell. At that moment, a spacecraft passes nearby. Its instruments cannot see the water's surface, nor can they know where individual ions are moving. The sensor records only that the magnetic field at this location does not perfectly match the expected value. A field line that should have followed a particular direction has been bent slightly. A small component appears within the signal, as though Europa is responding to the magnetic field sweeping across it. The entire journey can be held within one simple image. Jupiter's magnetic field enters the ice. The salty ocean responds with weak electrical currents. That response creates a new magnetic field that travels back outward. A sensor aboard the spacecraft listens for the difference. At no point does this process reveal the ocean in a photograph. No window opens onto the water. There is only an influence traveling inward, a response unfolding in darkness, and a signal returning in an altered form. This is the map to keep in mind as the story begins to shrink. Until now, everything has unfolded on the scale of Jupiter, Europa, and an ocean that may contain far more water than Earth sees. But the instrument used to recognize that change does not need to be equally large. A slightly bent magnetic field line can be detected by a sensor only a few millimeters wide. And deep inside that sensor, the part that actually responds to the magnetic field may be far smaller still, contained within an almost invisible defect in the otherwise orderly structure of a crystal. From here, the journey will leave the ocean and enter the interior of matter. From electrical currents extending around an entire moon, we will move toward electron spins, color centers in diamond and silicon carbide, and the way a tiny imperfection in a crystal lattice can listen for the trace of a watery world hidden beneath the ice. Magnetometers had been accompanying the exploration of space long before humanity began considering solid-state quantum sensors. They have flown past planets, entered the solar wind, measured disturbances within magnetospheres, and recorded how charged particles move around distant worlds. Through these instruments, completely invisible structures gradually became observable, not as images, but as sequences of numbers describing the strength and direction of the magnetic field at each point along a spacecraft's journey. A planet may appear quiet in photographs, yet a magnetometer reveals an environment in constant motion around it. Magnetic field lines are compressed on the side facing the sun and stretched into a long tail on the opposite side. Solar storms can shake the entire structure. Streams of plasma flowing through space create subtle variations that the human eye could never see. By measuring these changes, scientists can study planetary magnetic fields, the solar wind, and the interaction between charged particles and the upper atmosphere. Magnetometers also help us look inside celestial bodies. A planet's magnetic field may carry information about layers of conductive material moving deep within its core. A moon without a strong magnetic field of its own may still respond to the field of its parent planet, just as Europa responds to Jupiter's changing magnetic environment. Measurements made from outside can therefore provide clues about structures no drill could ever reach. Traditional sensors have performed this work extremely well. They have a long history of operation. Their principles are well understood, and they have proven capable of surviving many different space environments. Engineers know how to calibrate them, place them aboard spacecraft, and interpret the data they return. When a technology has become this reliable, the natural question is why NASA would still need to develop another generation. The answer is not that older magnetometers have become useless. It lies in the increasingly demanding requirements of future missions. A sensor that performs very well aboard a large spacecraft near Earth or Mars may not be the ideal choice for a small vehicle traveling into the outer solar system. Greater distances, longer journeys, and more limited resources make every gram of mass, every watt of power, and every small measurement error more important. In space, no component is truly carried for free. A heavier sensor requires a stronger spacecraft structure. A heavier structure may require more fuel. Additional fuel increases the launch mass. Changes that seem minor can spread throughout the entire mission design, affecting the launch vehicle, the power system, and even the ability to carry another scientific instrument. For small spacecraft, these limits become even more obvious. A platform closer in scale to a CubeSat does not have a large compartment for many bulky systems. The area available for solar panels is limited, the power source cannot provide unlimited energy, and the thermal control system must keep many instruments operating within a very small spacecraft body. Every sensor must prove that the data it provides are worth the mass and electrical power it consumes. Magnetometers also face a particular difficulty. They must measure a very weak field while sitting aboard a machine filled with electrical currents. Onboard computers, wiring, power converters, motors, and communication systems can all create magnetic fields of their own. When a scientific instrument tries to detect a subtle variation around Europa, the spacecraft itself may become the nearest source of interference. For this reason, magnetometers are often placed far from the main spacecraft body on a long boom. The distance helps reduce the influence of electrical systems and magnetic materials within the spacecraft. But the boom also has mass, requires a mechanism that can fold during launch, and must deploy correctly after the spacecraft reaches space. Every additional moving part creates another possible point of failure. Even when the sensor is placed far enough away, the interference does not disappear completely. Engineers must still map the magnetic field produced by the spacecraft, monitor the operating state of each system, and determine when a pump, transmitter, or small motor is affecting the data. Some disturbances last only a few seconds, while others unfold slowly over many months or years. Time itself is one of the most difficult challenges for distant missions. A journey to Jupiter already takes several years. Missions to Uranus or Neptune may require even longer travel, especially when their trajectories cannot take advantage of favorable gravitational assists. Many years may pass between the moment an instrument leaves the laboratory and the moment it begins making its most important measurements. During that time, materials age. Electronic components are exposed to radiation, connections pass through repeated cycles of heating and cooling. Parts that were calibrated with great precision on Earth may change slightly after a long journey. This gradual change is often called sensor drift. Imagine a clock that runs a few seconds faster than real time each day. On the first day, the error is almost unnoticeable. After a week, it still seems small, but over several months, the clock begins to run several minutes ahead. After many years, the user can no longer be sure whether the displayed time reflects reality or simply the error accumulated inside the mechanism. A magnetometer can experience a similar problem, although its drift may not occur as steadily as the error in a clock. The instrument's reference point may shift with temperature, component aging, or the amount of radiation it has absorbed. Its sensitivity may change by a very small amount. These changes do not cause the sensor to stop working, but they can shift its measurements away from their original values. On Earth, an instrument can be returned to a laboratory, placed beside a known standard, and recalibrated. A spacecraft near Jupiter has no such option. No engineer can open the spacecraft, inspect the sensor, and adjust a component that has drifted. Every method of testing must be built into the system in advance or rely on natural reference sources that can be recognized throughout the mission. The problem becomes even more serious when the signal being sought is extremely small. Suppose a magnetometer records a slight change in the magnetic field around Europa. Scientists need to know whether that change truly comes from the ocean beneath the ice, from Jupiter's plasma environment, or from the instrument itself, slowly drifting after years in space. When both the signal and the error are small, distinguishing between them may determine the entire scientific value of the measurement. Temperature also places pressure on the design. Space is often described simply as being extremely cold, but a spacecraft may experience many different thermal conditions. The side facing the sun may absorb energy, while the side in shadow cools rapidly. Instruments inside generate their own heat while operating. During a close pass by a planet or moon, the radiation environment and lighting conditions may change. A stable sensor must maintain a predictable response under all of these conditions. If every temperature change causes its reference point to shift, the system must carry better thermal controls, additional temperature sensors, and more complex correction models. Each solution requires more energy or adds more mass. Radiation presents another challenge. Near Jupiter, high-energy particles can damage electronic components, create unwanted electrical charges, or gradually alter the properties of materials. Some effects appear immediately, as temporary errors. Others accumulate slowly and become significant only after the instrument has been operating for a long time. Engineers can protect equipment with shielding, but shielding is heavy. The more radiation they want to block, the more material the spacecraft must carry. Another approach is to build sensors from materials that are naturally resistant to radiation, reducing the need for external protection. This is one reason silicon carbide has attracted attention for new devices. The material is already known for its ability to operate under harsh conditions, and the quantum defects within it create the possibility of using the crystal itself as the sensing element. The balance between sensitivity and durability is not simple either. The more sensitive a device becomes, the more likely it is to detect both the desired signal and unwanted noise. It may sense the magnetic field of an ocean, but at the same time, it may also respond to thermal fluctuations, interference from electrical systems, or tiny changes within its own structure. A good design does more than make the signal stronger. It must also help separate meaningful information from everything obscuring it. Existing magnetometers continue to be improved and used. The goal of solid-state quantum sensors is not to replace all previous technology immediately. Researchers are looking for another option, one that may provide competitive sensitivity in a system that is smaller, lighter, and consumes less power. For some missions, a traditional instrument may still be the best choice. For others, especially those using small platforms or traveling for many years, the advantages of a quantum sensor may become worthwhile. The word quantum can sometimes make this technology sound like a complete break from every instrument that came before it. In reality, all magnetometers depend on the way matter responds to magnetic fields, and all matter at its deepest level follows the laws of quantum mechanics. The difference is that these new sensors deliberately use individual quantum states that can be precisely controlled and read out, rather than relying only on the overall magnetic response of a larger component. One of the most important of these states is electron spin. Spin should not be imagined as a tiny sphere mechanically rotating around an axis. It is a quantum property that causes an electron to respond to a magnetic field through specific energy levels. It can be pictured as an extremely small compass needle, but one that does not simply rotate freely in every direction. It exists in distinct quantum states and can move from one state to another when it receives exactly the right amount of energy. The surrounding magnetic field changes the energy separation between these spin states. By measuring those extremely small shifts, scientists can determine the strength of the field. Instead of building a larger coil or using a stronger magnet, they use the subtle response of the electron as a measuring scale. This allows the part of the instrument that actually senses the magnetic field to become extraordinarily small. A complete device still requires a light source, electronic circuits, detectors, and a processing system, but the region of material performing the measurement may be only a few millimeters across. Within that crystal, the quantum centers actually involved in sensing exist on nearly the atomic scale. Small size offers several potential advantages. A lighter sensing element is easier to place aboard a small spacecraft. It may consume less power if the control and readout processes are designed efficiently. Several sensing elements could be arranged within one system to compare signals or remove interference shared by all of them. Manufacturing based on solid-state materials also creates opportunities for integration with electronic circuits in ways already familiar to the semiconductor industry. But the special advantage is not only size. Some quantum centers in crystals can contain both an electron spin and a nearby nuclear spin. These two systems interact in a highly stable way. The electron spin responds sensitively to the external magnetic field, while the nuclear spin can serve as an internal reference. The device can be imagined as carrying a measuring ruler within the material itself. Instead of recording a signal and simply hoping that the reference point has not changed, the system can compare the electron spin's response with a precisely defined quantum interaction. When temperature or another influence causes the sensor to shift, this comparison may help identify part of the error and correct the measurement. This ability is known as self-calibration, although that does not mean the device can correct every kind of error under every condition. It still needs to be tested, modeled, and combined with other calibration methods. But a reference built directly into the quantum structure of the material could reduce dependence on larger standards or external recalibration procedures that a spacecraft cannot perform during its journey. Returning to the image of a clock that gradually loses accuracy, a sensor with an internal reference is like a clock that can regularly compare its own rhythm with a standard oscillation preserved inside it. The error may not disappear entirely, but the device gains a way to recognize that it is drifting. During a mission lasting many years, this ability could help ensure that measurements made near the end of the journey still remain reliably connected to the original standard established on Earth. Long-term stability is especially important when a spacecraft makes repeated flybys of the same world. Scientists may want to compare a signal measured this year with one recorded several years earlier. The difference could reflect a new position within the parent planet's magnetic field or a change in the plasma environment. But for that comparison to be meaningful, they must know that the instrument itself has not changed too much between the two measurements. Smaller sensors could also change the way an entire mission is designed. Instead of relying on one large spacecraft carrying a single magnetometer, a mission might deploy several small vehicles at different locations. By measuring the magnetic field at multiple points at the same time, these spacecraft could reveal how the field varies across space, making it easier to distinguish an ocean signal from widespread disturbances in the surrounding plasma. This remains a possibility under active study, not a system ready to replace every existing mission. Sensitivity achieved in the laboratory must be transformed into stable sensitivity aboard a real spacecraft. Lasers, microwave circuits, or electrical readout systems must survive the vibration of launch. The device must operate in vacuum, radiation, and changing temperatures. Every theoretical advantage matters only if the complete system can survive in space. A quantum sensor is not automatically immune to noise either. Electron spins may respond not only to magnetic fields, but also to temperature, pressure, or electric fields. This property is useful when creating different kinds of sensors, but in a magnetometer, these unwanted influences must be separated. Material design, readout methods, and processing algorithms must all work together to identify the part of the change that is truly caused by magnetism. Despite the remaining challenges, this direction is compelling because it addresses several limitations of distant missions at once. Solid-state crystals can be small and durable. Quantum centers may operate at room temperature rather than requiring a bulky deep cooling system. Some materials can withstand radiation and extreme temperatures. The interaction between electron spins and nuclear spins offers an internal reference mechanism that may help control drift. At the largest scale, the mission is still to find an ocean beneath many kilometers of ice. At the scale of the instrument, however, the solution may lie in measuring the energy separation between quantum states too small to be seen. A very weak magnetic signal passes through the ice, reaches the spacecraft, and slightly changes the behavior of electrons inside a crystal. This shift in scale does not happen by making the magnetic field stronger. Humanity cannot ask Europa's ocean to send a clearer signal. It can only build a tool that listens more carefully, drifts less over time, and remains small enough to be carried to places that larger spacecraft may struggle to reach. To do this, scientists turn towards something that conventional material manufacturing often tries to eliminate. In an ideal crystal, atoms are arranged in an evenly repeating order, but real crystals are rarely perfect. One atom may be missing. Another may occupy the wrong position. The structure around that imperfection can trap electrons with unusual spin states. In many situations, this is simply a defect. But from the perspective of quantum physics, that defect can become a sensor. The new technology, therefore, does not begin with a large magnet, a long coil, or a heavier instrument. It begins with a tiny empty space in a crystal lattice, where an atom should have been, but is not. A missing atom in a crystal may seem like nothing more than a tiny flaw. In a piece of material containing an almost unimaginable number of atoms, that empty site appears insignificant. But at the quantum level, a vacancy can change how electrons are distributed, how they absorb light, and how they respond to magnetic fields. What is usually treated as an imperfection in material fabrication can become the most sensitive part of an entire scientific instrument. To understand how this is possible, begin with the image of a nearly perfect crystal. In a crystalline material, atoms are not arranged randomly like grains of sand poured into a box. They form an ordered pattern that repeats through space. Each atom occupies a relatively stable position in relation to its neighbors, creating a structural lattice that extends throughout the material. Diamond is a familiar example. Each carbon atom bonds with the carbon atoms around it in an extremely stable structure. This order helps give diamond its hardness, transparency, and many unusual properties. Silicon carbide is also a crystalline material, but its lattice is made of silicon and carbon arranged in specific patterns. It is known for its ability to withstand heat, radiation, and environments in which many conventional semiconductor materials struggle to operate. A perfect crystal exists only in a model. Real materials always contain small irregularities. An atom may be missing from the position where it should have been. Another atom may replace the original type by mistake. Two vacant sites may appear next to each other. A foreign atom may sit beside a vacancy, and together they can form a new structure within the crystal lattice. Imagine a tiled floor laid so evenly that every tile is identical and perfectly positioned. From a distance, the entire surface forms a complete repeating pattern. But in one place, a tile is missing. That empty space does more than remove part of the floor. It also changes how forces are distributed among the surrounding tiles. When the floor is exposed to vibration, the area near the gap may respond differently from the rest. Color centers in crystals can be pictured in a similar way. The term color center comes from the fact that certain defects can absorb or emit specific wavelengths of light, giving the material a color different from that of a perfect crystal. In natural gemstones, foreign atoms and defects in the crystal lattice can help produce the colors we see. A colorless diamond and a colored diamond may both be made primarily of carbon, yet very small differences in their internal structures cause them to interact with light in different ways. In the laboratory, the value of a color center goes far beyond color. Electrons bound around the defect can occupy relatively stable quantum states. These states respond to the surrounding environment, especially to magnetic fields. By learning how to prepare, control, and read them, scientists can turn a color center into an extremely small sensor. One widely studied defect in diamond forms when a carbon atom is replaced by a different kind of atom and a neighboring carbon site is left empty. This combination creates an electronic structure, unlike the rest of the crystal. The electrons around the defect no longer behave like those in a perfect diamond lattice. They have energy levels and spin states that can be influenced by light, microwave signals, and magnetic fields. It is not necessary to remember the specific name of every defect in order to understand the principle. What matters is that a very small region inside the crystal has become a quantum system capable of detecting external changes. Most of the diamond still serves as a hard, stable host material. The color center inside it acts like a sensing point protected by the surrounding crystal lattice. The property commonly used to measure magnetic fields is electron spin. The word spin can easily suggest an image of a tiny particle rotating around its own axis, like a miniature planet. But that is not an accurate description. An electron is not a solid sphere turning like a wheel. Spin is an intrinsic quantum property expressed through the electron's magnetic moment and the way it responds to a magnetic field. For the moment, spin can be imagined as an extremely small compass needle, since both respond to magnetic fields. A normal compass needle, however, can rotate continuously through many angles. Quantum spin allows only certain defined states when measured along a particular direction. It does not simply choose any angle between those states. This discrete behavior creates energy levels that can be measured with extraordinary precision. In the absence of an external magnetic field, some spin states may have equal or nearly equal energies. When a magnetic field is present, it interacts with the electron's magnetic moment and separates those energy levels. The stronger the magnetic field, the more the spacing between certain levels may change. By measuring that energy difference precisely, scientists can determine the strength of the magnetic field at the location of the color center. The process can be compared to a musical instrument with specific resonant notes. As the surrounding conditions change, the pitch of some notes shifts very slightly. An ordinary listener may not notice, but a precise acoustic instrument can detect the change. In a color center, the note is the frequency required to move the spin from one state to another. The magnetic field shifts that resonant frequency, and the shift becomes the measured signal. To determine which state the spin is in, scientists need a way to deliver energy to the system, and another way to read its response. Light is one of the most effective tools for doing this. When a laser of the appropriate wavelength is directed into the crystal, the color center absorbs energy and then emits light at a different wavelength. The intensity of that emitted light depends partly on the spin state of the electrons around the defect. In a diamond sensing system, a green laser can be used to excite the color centers. The crystal then emits light at longer wavelengths. An optical detector records the intensity of this light. At the same time, scientists apply a microwave signal and vary its frequency, allowing them to identify the frequencies that cause the spin state to change. At these resonant points, the brightness of the light emitted by the crystal changes by a small but measurable amount. From the positions of these resonant points, the system can determine the surrounding magnetic field. The entire measurement can take place without observing individual electrons. Many color centers within a crystal respond together, producing a combined optical signal strong enough for a detector to record. The sensing element still operates at the atomic scale, but its response is amplified into a change in light that electronic systems can process. Silicon carbide also contains quantum defects that work through a similar principle. In some systems described by NASA, this material can be excited using deep red light. The defects absorb the light. Their electronic states are prepared in a controlled way, and the optical response carries information about their spin. The wavelength differs from that used for diamond because the energy structures of the defects and the host materials are not the same. Using a green laser for diamond or deep red light for silicon carbide is not a choice based on visual color alone. Each color center absorbs and emits efficiently only within certain wavelength ranges. The light source must match the energy spacing between the system's levels. With the correct wavelength, light can both prepare the spin in the desired state and help read that state through the emitted signal. The process of guiding the system into a preferred spin state is often called optical pumping. Light continuously excites the electrons, and through repeated cycles of absorption and emission, most of the system is directed into a particular quantum state. A microwave signal or a magnetic influence then changes the distribution among the states. That change is reflected in the light emitted by the crystal. This is not a process that can be seen with the naked eye. The crystal does not necessarily glow or visibly change color each time the magnetic field varies. The difference in luminescence intensity may be extremely small. Optical detectors, amplification circuits, and processing algorithms must combine many measurements to separate the signal from the noise. Color centers offer an important advantage because many systems in diamond and silicon carbide can preserve useful quantum properties at room temperature. Many other quantum technologies work well only when cooled to temperatures near absolute zero. Producing such extreme cold is already complex in a laboratory, and aboard a spacecraft it would require additional cooling systems, insulation, and power. A sensor that can operate without deep cooling is easier to make compact. This does not mean that it is completely unaffected by temperature. Heat can still shift energy levels, alter brightness, and reduce accuracy. But the instrument does not need a bulky cryogenic chamber simply to preserve its basic quantum behavior. The crystal lattice also helps protect the color centers. The electrons do not drift freely through a vacuum, but remain confined within a stable material environment. Diamond has a strong structure and conducts heat efficiently. Silicon carbide can withstand high temperatures, radiation, and many harsh conditions. These properties make both materials attractive candidates for sensors designed for space. However, sensitivity to the environment is both an advantage and a challenge. Spins around a color center may respond to magnetic fields, but they can also be influenced by temperature, pressure, mechanical strain, and electric fields. The same shift in a signal can sometimes have several different causes. It is like an extremely sensitive bell that can ring in response to sound, but also when heat causes the metal to expand or when the table beneath it moves. To use that bell to measure one specific influence, the researcher must learn how to recognize and remove the others. In quantum sensors, this can be done in several ways. Scientists may measure multiple spin transitions at the same time because magnetic fields and temperature do not always shift them in the same pattern. They can orient color centers along different directions within the crystal to determine the direction of the magnetic field. Additional temperature sensors and pre-flight calibration can also help separate magnetic signals from environmental changes. The ability to respond to several physical quantities is not only a limitation. It also makes color centers a platform for many kinds of sensors. The same crystal can be used to study magnetic fields, temperature, pressure, electric fields, or strain, depending on how the system is designed and which signals are analyzed. In an ocean detection application, the goal is to optimize the instrument for magnetism and control the other influences well enough that they do not obscure the signal being sought. The sensing crystal may be only a few millimeters across, yet it can contain a very large number of color centers. A greater number of centers increases the amount of emitted light and can make the measurement easier to perform. Even so, adding more defects does not always improve the sensor. When color centers are too close together, they can interact, create interference, and cause the spin states to lose stability more quickly. Manufacturers must therefore control the density of defects, the purity of the crystal, and the atomic isotopes present within the material. Surrounding atoms with nuclear spin also create extremely small magnetic fields, forming a kind of background noise at the quantum level. In some designs, this noise must be reduced. In others, a stable nuclear spin can be used as a reference to support self-calibration. A useful color center must do more than respond sensitively to a magnetic field. Its spin state must also persist long enough to be controlled and measured. If the environment causes the state to lose order too quickly, the information about the magnetic field will disappear before the system can read it. The length of time over which the quantum state preserves the necessary relationship is often called the coherence time. There is no need to go deeply into the mathematics to understand why this matters. Imagine a group of tiny compass needles initially aligned in the same direction. Over time, environmental noise causes each needle to drift differently, and their synchronization gradually fades. The sensor must complete its sequence of preparation interaction, and read out before too much of that order is lost. Pure diamond can provide a relatively quiet environment for certain color centers, allowing their spin states to persist long enough for precise measurements. Silicon carbide offers different advantages in manufacturing, durability, and electronic integration. No material is perfect in every respect. Research teams must balance sensitivity, stability, manufacturability, and the conditions of the mission. Another advantage of silicon carbide is that it is already widely used in the high-power semiconductor industry. Techniques for producing wafers, etching microscopic structures, and fabricating electronic components are relatively well developed. This creates the possibility of integrating the quantum sensing element with its readout circuitry in a smaller system, rather than placing a separate crystal beside a collection of bulky optical components. In an optical readout system, the device requires a laser source, components that guide and collect light, and circuits that process the signal. The laser must remain stable over many years. The detector must recognize extremely small changes in intensity, and the entire optical path must survive the vibrations of launch. Achieving high sensitivity in a laboratory is only the first step. The system must also be miniaturized and made durable enough for the space environment. The states of these defects can also be read electrically. Instead of measuring the amount of light emitted, the system tracks changes in electric current or charge associated with the spin state. In some defects, the processes that create and transport charge through the material depend on spin. When the spin state changes, the measured electrical signal changes as well. Electrical readout could reduce the number of optical components that need to be carried. There would be no need to collect individual photons emitted by the crystal through a complex system of lenses. The signal could be fed directly into electronic circuits and processed using methods more familiar to semiconductor technology. This could make the device smaller, lighter, and easier to integrate. But electrical readout presents challenges of its own. The spin-related currents may be extremely weak. Electrical contacts with the material must be fabricated with great precision. Electronic noise and changes in temperature can obscure the signal. The system must distinguish the charge truly associated with the spin state from leakage currents and every other fluctuation within the device. Optical readout often has an advantage in sensitivity because light allows the spin state to be prepared and observed more directly. In return, it requires a laser source, filters, and optical detectors. The two approaches are therefore not simply a matter of one being better and the other worse. Each creates a different balance between sensitivity, size, complexity, and power consumption. In both cases, the underlying principle remains the same. An external magnetic field changes the energy levels of the spin. The system prepares the spin in a known state, allows it to interact with the environment, and then reads how that state has changed. The response is converted into light or electric current, and then into digital data that the spacecraft can store and transmit back to Earth. A sensor like this does not directly know whether it is flying past Europa or sitting inside a laboratory. It simply responds to the magnetic environment at the location of the crystal. The planetary meaning comes later, when the data are connected to the spacecraft's position, models of Jupiter's magnetic field, and the expected structure of the Moon. This is the bridge between the quantum world and an ocean beneath the ice. An induced current, extending around Europa, creates a secondary magnetic field. That field enters the crystal aboard the spacecraft and changes the energy separation between spin states by an extremely small amount. Light or electronic circuits read that shift and turn it into a signal scientists can analyze. There is no mysterious connection between the ocean and the color center. There is only an unbroken chain of physical interactions. Salty water allows ions to move. Electric currents generate magnetic fields. Magnetic fields act on the magnetic moments of electrons. Spin energy levels shift. Optical or electrical signals change. Each step is small, but together they allow an atomic scale defect to carry information about an ocean the size of a world. The imperfection in the crystal therefore becomes an advantage. In a completely uniform lattice, electrons are bound in ways that make it difficult to isolate them as a controllable sensing system. A defect creates a region with a distinctive energy structure, like a small room formed inside a building that repeats endlessly. Within that room, spin states can be prepared, influenced, and read. A missing tile causes the area around it to respond differently from the rest of the floor. A missing atom likewise causes the surrounding electronic region to respond differently from the rest of the crystal. The difference is that instead of measuring forces across a floor, scientists measure light, electric current, and shifts between quantum energy levels. From a small imperfection in a material, humanity can build a compass without a needle, an instrument that does not need to observe mechanical motion but can still detect a magnetic field. And because spin states can be measured with great precision, this compass has the potential to sense the extremely weak distortions created by an ocean beneath the ice. JPL is currently pursuing this same quantum principle along two different paths. One device favors electrical readout in silicon carbide, aiming for a compact structure and a high degree of integration. The other uses light to prepare and read the spin states, accepting a more complex optical system in pursuit of greater sensitivity. Both paths begin with the same idea. A defect in a crystal is not necessarily something that must be eliminated. When it is created in the right way and placed within a suitable measurement system, it can become an element that listens to magnetic fields. From this idea comes SICMAG and Opus Magnum, two devices that are attempting to transform extremely small quantum states into tools for searching for extremely large oceans. Starting from the same foundation of quantum color centers in crystals, engineers at JPL are pursuing two different paths for turning the responsive spin into a magnetic field measurement that can be used aboard a spacecraft. One approach prioritizes compact size and ease of integration by reading the signal electrically. The other uses light to prepare and observe the quantum state, accepting a more complex system in pursuit of greater sensitivity. These two devices are known as SICMAG and Opus Magnum. SICMAG stands for silicon carbide magnetometer, a magnetometer that uses quantum defects in silicon carbide. This material is already familiar to the electronics industry. It has been used in components designed to withstand high temperatures, high voltages, and harsh environments. But in SICMAG, the value of silicon carbide lies not only in its durability. Missing atoms or unusual arrangements within the crystal lattice can hold spin states that are sensitive to magnetic fields, creating a sensing element on an extremely small scale. What makes SICMAG especially notable is the way it reads those states. Instead of collecting light emitted by the crystal through a system of lenses and optical detectors, the device attempts to convert the spin response into an electrical signal. When the quantum state around a color center changes, the movement of electric charge through the material also changes slightly. Electrodes and readout circuits can detect that variation and convert it into digital data. The crystal can be imagined as an extremely sensitive electronic component with an additional layer of quantum information inside it. The current flowing through the device depends not only on the voltage applied across it, but also on the spin states of defects within the crystal lattice. An external magnetic field shifts the spin energy levels. That shift alters the electrical response. The measurement circuit records the change and uses it to determine the strength of the surrounding magnetic field. This chain of interactions does not require a large photon detector or a complicated optical path. That is an important advantage for a device that needs to be miniaturized. Aboard a spacecraft, every lens, mirror, optical fiber, and alignment component occupies space and must survive the vibrations of launch. A system that relies mainly on electrical readout could reduce the number of these components, bringing the sensor closer in form to a conventional semiconductor device. This does not mean that SICMAG requires no light or other control signals in every possible configuration. The color centers must still be prepared and manipulated correctly so that their spins carry information that can be read. But the goal of this design approach is to make the final signal detection process more closely resemble solid-state electronics, with electric current collected directly and processed within the circuitry. A device like this has the potential to become smaller, lighter, and less power-hungry than a complete optical system. It may be well suited to spacecraft with very limited room, where a large compartment cannot be devoted to a sensor and its supporting equipment. On a small vehicle, eliminating even a few lenses, a large optical detector, or a precision alignment system can make a meaningful difference to the entire design. However, a simpler physical form does not make the measurement itself easy. The electrical signals associated with spin states can be extremely weak. Leakage currents within the material, noise from the circuitry, temperature changes, and small fluctuations in the power supply can all obscure the response being sought. An electrical readout device must be sensitive enough to recognize the change produced by spin without confusing it with the countless other electrical variations occurring within the component. This is a familiar challenge in sensor science. When the desired signal is very small, the hardest task is not merely making it appear, but knowing with confidence where it came from. A change in current may be caused by a magnetic field shifting the spin states, but it could also result from a slight rise in temperature, making the material more conductive. The processing system must separate these effects through careful design, calibration, and repeated measurements. Silicon carbide provides a suitable material platform for this goal because it can tolerate conditions that challenge many other semiconductors. During a journey into the outer solar system, a sensor may have to endure radiation, changing temperatures, and many years of continuous operation. A durable material does not eliminate every problem, but it reduces the risk that the crystal itself will change too quickly before the spacecraft reaches its destination. SICMAG therefore represents a path focused on practical system design. Instead of trying to produce the strongest possible optical signal, the device seeks to place the quantum sensing element within a compact electronic structure that is easier to integrate. The goal is not only to achieve good sensitivity in the laboratory, but to achieve useful sensitivity in an instrument small enough to fly aboard a compact spacecraft. OPUS Mag-M follows a different path. This device uses optical pumping, meaning that light is used to prepare the spin states within the crystal before their response is read. Rather than monitoring only electric current, the system observes how the crystal absorbs and emits light as its quantum states change. In a configuration like this, a laser beam is directed toward the sensing crystal. The wavelength is selected to match the type of color center being used. For certain color centers in diamond, green light can raise electrons into higher energy states. In silicon carbide, the system may use deep red light. After absorbing energy, the electrons return to lower energy states and emit light with properties that depend on their spin. Optical pumping does more than make the crystal emit light. It helps guide many color centers into the same preferred quantum state, much like aligning a group of tiny compass needles in the same direction before beginning a measurement. The surrounding magnetic field then changes the spacing between the spin states. A microwave signal is swept across a range of frequencies to find the points where the spins change state. When resonance occurs, the intensity of the light emitted by the crystal shifts slightly. An optical detector records these changes. From the resonant frequencies and the shape of the signal, the system determines the magnetic field at the crystal's location. This method takes direct advantage of the connection between spin and light, one of the most extensively studied properties of many quantum color centers. The major advantage of optical readout is its potential sensitivity. Light can be collected from a very large number of color centers at once, amplifying the response of extremely small quantum systems into a signal that a detector can record. Very slight changes in spin state can produce a measurable difference in the amount of light emitted. In return, the system requires more components. The laser must produce stable light at the correct wavelength. Optical elements must guide the light toward the crystal and collect the response. Filters must remove the much stronger excitation light, so the detector can recognize the weaker luminescent signal. The detector must be sensitive enough to measure very small changes, while also surviving radiation and remaining stable for many years. On a laboratory bench, these components can be placed on large mounts and adjusted by hand. Aboard a spacecraft, the entire system must be miniaturized, secured firmly, and kept aligned after enduring the intense vibration of launch. Even a slight shift in a lens can reduce the amount of light reaching the crystal. A laser whose wavelength changes with temperature can make optical pumping less effective. For this reason, OPUS MAGNM is not simply a diamond placed beneath a laser while its brightness is measured. It is a coordinated system of quantum material, a light source, microwave signals, optical detectors, control electronics, and analysis algorithms. Every component must remain stable enough for the final signal to reflect the magnetic field in space rather than changes occurring inside the instrument. That complexity is accepted because greater sensitivity could provide major scientific benefits. The induced signal from an ocean beneath the ice is often far weaker than the magnetic field of the parent planet and the surrounding plasma fluctuations. A more sensitive sensor may detect subtle details in the field's shape and rhythm, allowing the ocean to be modeled more accurately. It may help distinguish a broad conductive layer of water from a smaller region or compare magnetic responses recorded during different flybys. Greater sensitivity does not automatically resolve every ambiguity in the models, but it provides richer data that can be considered alongside radar, gravity measurements, and geological images. SICMAG and OPUS Magnum are therefore not two instruments performing exactly the same task through completely equivalent methods. They represent two different balances. SICMAG aims for a more compact electrical readout system with strong integration potential, making it suitable for platforms limited in space, mass, and power. OPUS Magnum uses a more complex optical system, but may be able to push sensitivity higher. Neither path is naturally superior for every mission. A small spacecraft may prioritize simplicity and low power consumption. A larger spacecraft seeking to measure extremely weak magnetic fields may accept a heavier optical system in exchange for greater sensitivity. Engineers must choose according to the trajectory, the duration of the journey, the radiation environment, and the type of scientific signal being sought. Inside JPL laboratories, these trade-offs are tested on a scale far smaller than the planets and moons the sensors may one day study. The optical sensing element may be a crystal only a few millimeters wide. It is small enough to rest on a fingertip, yet it contains countless atomic-scale color centers responding to magnetic fields. A crystal this small cannot be tested accurately if it is placed directly within the ordinary magnetic environment of a laboratory. Earth has a magnetic field of its own. Electrical wiring in the walls, electronic equipment, motors, elevators, and many other sources also create small variations. To humans, these fields are completely unremarkable. To a sensor designed to detect an extremely weak signal, they may be far larger than the response being measured. The crystal is therefore placed inside a magnetically shielded chamber made from several layers of material. Each layer helps redirect or weaken part of the external magnetic field. When the layers work together, the influence of Earth's field and nearby sources can be reduced by roughly a factor of 100,000. This does not mean that the chamber contains no magnetic field at all. Creating an environment with absolutely no magnetic field is nearly impossible in practice. The goal is to make the background interference small and stable enough for the research team to know precisely which field is acting on the sensor. They can then generate extremely weak test fields and observe how the crystal responds. The contrast inside that room nearly captures the entire idea behind the technology. Outside the shielded chamber is Earth's magnetic field, a planetary field extending tens of thousands of kilometers into space. Inside is a crystal only a few millimeters across. Within that crystal are defects far smaller still, created by a missing atom or an atom occupying the wrong position. Researchers shine light into the crystal, send microwave signals through it, or place electrodes on the material. They change the test magnetic field by an extremely small amount and then monitor how the light or electric current responds. Each measurement helps determine the system's sensitivity, noise level, and stability. A good sensor must do more than respond strongly to a magnetic field. It must respond in the same way when the measurement is repeated. If the same field produces different results after only a few hours, the device will be difficult to use on a long mission. The tests, therefore, do not examine only the weakest field the sensor can detect. They also track drift over time, the effects of temperature, and the way components change during continuous operation. The research team must also determine whether the signal comes from the color centers or from another part of the system. In an optical device, the laser power may fluctuate slightly. The detector's sensitivity may change with temperature. In an electrical device, the power source and amplification circuits may introduce noise of their own. Every component must be measured and modeled before the quantum response can be isolated with confidence. This is why a quantum device can appear small, while its development remains far from simple. The atomic scale sensing element is only the center of a much larger system. Turning the spin response into scientific data requires a way to prepare the state, generate reference fields, read the signal, remove noise, and keep everything stable under harsh conditions. Tests inside the shielded chamber also reproduce part of the challenge a spacecraft will face. In space, the sensor will not be surrounded by a quiet room. It will sit beside computers, wiring, and components producing magnetic fields of their own. Outside the spacecraft will be plasma, radiation, and a planetary magnetic field that is constantly changing. The instrument must distinguish the scientific signal from both groups of interference. One way to do this is through multiple reference measurements. The sensor may measure along different directions or use several color centers with different orientations within the same crystal. The system may also compare the response of electron spins with more stable nuclear spins, helping it recognize when its reference point is drifting. These techniques are still being studied to determine how reliably they can operate in a practical device. NASA has supported the development of solid-state quantum magnetometers through the Picasso program since 2016. This program supports scientific instrument technologies that are still at a relatively early stage, helping promising ideas move from the laboratory toward a level where they can be considered for future missions. This also means that SICMAG and OPUS Magnum are not yet complete instruments flying through space. They are not sensors currently operating aboard a spacecraft bound for Europa, nor have they been fully proven over a multi-year journey through a radiation-filled environment. Laboratory results reveal their potential, but many steps still separate a prototype from an instrument qualified for flight. The devices must endure launch-like vibration, vacuum testing, thermal cycling, and radiation exposure. Their optical or electronic components must preserve their alignment and performance afterward. The processing software must run on hardware with limited power, and the entire system must be designed so that it does not generate too much magnetic interference and disturb the very measurements it is trying to make. Miniaturization matters only if sensitivity is preserved. A very small sensor with too much noise will not help find an ocean. An extremely sensitive instrument that consumes too much power or begins drifting after only a few months would also be poorly suited to a distant mission. Success lies in balancing sensitivity, size, mass, power consumption, and durability. In the laboratory, the crystal only needs to operate within a controlled environment. In space, it may have to wait many years before making its most important measurement. During that time, the laser must maintain its wavelength, the electrodes must remain undamaged, the detector must not lose too much sensitivity, and the quantum defects must continue responding in the way they were originally calibrated. There is a vast engineering distance between an atomic scale vacancy and an instrument traveling between planets, yet closing that distance is precisely what these research teams are trying to accomplish. SICMAG seeks to place spin states within a more compact electrical readout system. OPUS MAGNM aims to use light to achieve a more sensitive signal. Both are attempting to turn a defect in a material into a magnetic field standard stable enough for planetary science. At the other end of the measurement may be an ocean buried beneath kilometers of ice. That ocean does not know that a crystal is waiting to detect it. Its ions simply respond to the magnetic field of the parent planet as they have for billions of years. The induced currents generate a secondary magnetic field, and that field spreads into space as an extremely subtle distortion. A spacecraft passes at the right moment. The magnetic field reaches the crystal. The spacing between spin states changes. An electric current shifts by a tiny amount, or an optical signal becomes slightly weaker. From that change, the instrument records a number. Many numbers combine into a line of data. That line enters a model, and the ocean begins to appear. This is the promise of SICMAG and OPUS MAGNM, not to see the water, but to sense its response through a chain of interactions extending from the planetary scale down to the atomic scale. A small instrument could become a bridge between those two extremes, but only if it is durable enough to survive the journey, stable enough not to confuse its own drift with a real signal, and sensitive enough to recognize the ocean within the noise of the surrounding environment. The next question, then, is no longer simply whether a crystal can measure a magnetic field in a laboratory. The more important question is whether that technology can leave the shielded chamber, survive the vibrations of launch, withstand radiation, and continue operating after years in space. Only then will atomic-scale defects truly have a chance to listen for oceans hidden beneath the ice of distant worlds. A sensor only a few millimeters wide does not automatically become a planetary exploration instrument simply because it performs well in a laboratory. Between the magnetically shielded room at JPL and the environment surrounding a distant world lie a rocket launch, vacuum, radiation, repeated cycles of heating and cooling, and a journey that may last for many years. Every component must survive that entire distance without any human hand reaching it to adjust, replace, or repair it. Only after enduring the full journey will the quantum crystal have a chance to make the measurement it was designed to perform. The advantages of solid-state quantum magnetometers begin with their size. The sensing element can be extremely small compared with many traditional magnetometer systems, while the complete instrument is expected to have lower mass and power consumption. Diamond and silicon carbide also allow color centers to operate at room temperature, withstand radiation, and function across a wide range of temperatures. The interaction between electron spins and nuclear spins also creates the possibility of self-calibration, helping the instrument recognize and compensate for some of the drift that accumulates over time. NASA considers these characteristics especially useful for missions lasting several decades to the region of the ice giant planets. A smaller size does more than reduce the mass of the sensor itself. It may change the structure of the entire spacecraft. Traditional fluxgate magnetometers are often mounted on a long boom to move them away from magnetic fields generated by the spacecraft. Such a system requires sensors, a deployable boom, a folding mechanism, wiring, and extensive testing before launch. Europa Clipper, for example, carries 3 fluxgate sensors on a boom approximately 8.5 meters long, allowing them to measure the external magnetic field while reducing interference from the spacecraft body. A sufficiently small solid-state sensor could allow multiple measurement points to be placed around a spacecraft. Instead of mounting only 1 or 2 sensors far from the main body, engineers could imagine a network of small sensors, each recording the magnetic field at a different location. By comparing these measurements, The system could identify the part of the field that decreases with distance and is therefore likely to have been produced by the spacecraft itself. What remains would be more consistent with the external space environment. SICMAG is being studied with this possibility in mind. NASA has stated that the silicon carbide sensing element could be extremely small, and that several sensors might be placed on the same spacecraft to help remove magnetic interference from the vehicle, provide redundancy, and reduce the need for a long magnetometer boom. This remains a technological possibility, dependent on the system achieving the required sensitivity and operating reliably under real flight conditions. These benefits are especially clear for small spacecraft. A CubeSat does not have room to carry every structure originally designed for a large vehicle. It has limited solar panel area, less capacity for heat dissipation, and very little mass available for each instrument. When a sensor is made smaller, the saved mass can be used for communications, power systems, or another scientific instrument. Every watt of power that can be saved also gives the spacecraft greater ability to operate during periods when energy becomes scarce. NASA has suggested that new quantum sensors may be able to reduce instruments once suitable only for large missions to a cost and size closer to a CubeSat platform, while still aiming for measurements of high scientific value. This describes an ambitious development goal, not a capability that has already been fully demonstrated aboard a small spacecraft in space. SICMAG and Opus Magnum are still being developed, tested, and refined before they can be selected for a specific mission. Between a laboratory prototype and a flight-qualified instrument lie many steps that are rarely seen. First, the sensor must be shaken at levels similar to the forces produced when a rocket leaves the launch pad. An optical connection that works perfectly on a laboratory bench may become misaligned after only a few minutes of intense vibration. A tiny electrode may crack. A wire connection may change its resistance. Damage like this does not always cause the instrument to shut down completely. Sometimes it creates only a small error, yet one large enough to reduce the value of measurements made many years later. After vibration testing comes vacuum testing. On Earth, air helps carry heat away from components. In space, that form of heat transfer almost disappears. The instrument must conduct heat into other parts of the spacecraft and then release it outward as radiation. A laser, amplifier circuit, or optical detector that operates normally in air may become warmer than expected when placed in a vacuum. Thermal cycles are also repeated again and again. The instrument is cooled, heated, and then cooled once more to simulate the different conditions it may experience during the journey. Metals, crystals, adhesives, and coatings do not expand in exactly the same way. After many cycles, small stresses can accumulate where different components meet. Optical systems are especially sensitive to changes in geometry because even a tiny shift can cause the laser beam to miss the region of the crystal being measured. Radiation presents a longer-term challenge. High-energy particles can penetrate components, alter electrical charge, create errors in memory circuits, or gradually degrade materials. Silicon carbide has attracted attention partly because it can tolerate radiation and extreme temperatures better than many conventional electronic materials. But the durability of the host material alone does not guarantee that the entire magnetometer will survive. The laser, light detector, controller, and accompanying electronics must also be tested. Self-calibration becomes valuable under these conditions. After many years, a sensor may still be operating, even though its reference point has shifted. If the instrument can compare the response of electron spins with a more stable nuclear spin interaction, it gains an additional measuring standard built directly into the material. That standard does not remove every source of error, but it may help distinguish some changes within the instrument from genuine variations in the magnetic environment. This is especially important in the outer solar system. A spacecraft traveling to Uranus or Neptune may spend most of its operational life simply reaching its destination. During those long years, the sensor will continue to experience radiation, thermal cycling, and the natural aging of its components. When the spacecraft finally arrives, scientists must know that the magnetic field values it records can still be connected to the reference established before it left Earth. NASA has emphasized that decades-long missions to the ice giants are precisely where self-calibration and resistance to drift may become particularly valuable. Those distant planets are compelling for more than their size or color. Their magnetic fields preserve information about the structure and motion deep within them. Uranus and Neptune have unusual magnetic fields, with strongly tilted magnetic axes and field centers that do not align neatly with the centers of the planets. To understand where these fields are generated, how conductive materials move inside, and how the planets evolved, a spacecraft must measure the magnetic environment from many locations over long periods of time. Magnetometers also track how a planet's magnetosphere interacts with the solar wind. On the side facing the Sun, the magnetosphere may be compressed. On the opposite side, it stretches into a broad, tail-like region. As conditions in the solar wind change, the entire structure responds. A sensor operating continuously can help reconstruct those changes and distinguish the planet's intrinsic characteristics from influences coming from the external environment. Moons within a magnetosphere create disturbances of their own. A moon with a thin atmosphere, a conductive surface, or an ocean beneath the ice can redirect plasma flow and distort the magnetic field. Measuring these changes allows scientists to study the planet, its moons, and the surrounding plasma environment at the same time. A magnetometer therefore serves more than a single question about water. It becomes a tool for exploring the entire system. For icy moons, induction measurements may continue to be used to search for conductive layers of liquid. Not every world offers conditions as favorable as Europa. The magnetic field of the parent planet may be weaker, change more slowly, or become mixed with many other forms of interference. For that reason, sensor sensitivity, the ability to measure in multiple directions, and long-term stability become even more important. A network of small spacecraft could offer a different way of observing these environments. Instead of a single spacecraft flying past and moving on, several vehicles could measure the magnetic field from different locations at the same time. When a plasma disturbance sweeps across the entire region, every sensor would record a related pattern of change. A disturbance appearing only near one moon might reveal a local source. This comparison would help separate variations over time from variations across space, a problem that is extremely difficult to solve with only one spacecraft. This is one reason the idea of placing advanced science on smaller platforms is so appealing. A large spacecraft can carry more capable instruments, a stronger power supply, and a more powerful long-distance communication system. But a group of small spacecraft can spread through space. Together, they can create multiple observation points, accepting that each individual vehicle is simpler, while the entire network provides a picture no single spacecraft could obtain. That possibility still lies in the future. A CubeSat operating near Earth is very different from a small spacecraft traveling to Jupiter, Uranus, or Neptune. Solar energy decreases sharply with distance. Communication becomes slower and weaker. Components must operate autonomously for long periods with little direct support. Miniaturizing the sensor solves only part of the problem. The spacecraft still needs power, trajectory control, radiation protection, and an antenna capable of sending data home. While these technologies are still being developed, a major mission has already begun its journey to Europa. Europa Clipper launched on the 14th of October 2024. The spacecraft is traveling roughly 2.9 billion kilometers and is expected to reach the Jupiter system in April 2030. After entering orbit around Jupiter, it will make 49 close approaches to Europa. Europa Clipper carries 9 scientific instruments, along with a gravity experiment that uses the spacecraft's communication system. These instruments are designed to complement one another during the flybys, studying Europa's ice shell, surface composition, geology, plasma environment, and internal structure. The central goal is not to search directly for organisms, but to determine whether places beneath Europa's surface may contain conditions suitable for supporting life. The scale of Europa Clipper shows that studying an ocean world still requires a very large system. With its solar arrays deployed, the spacecraft spans more than 30 meters, nearly the length of a basketball court. Within it are power, communication, thermal control, radiation, protection, and a collection of instruments that must all operate together in Jupiter's intense environment. Cameras will map the surface at higher resolution than previous missions. Spectrometers will study the distribution of ice, salts, and other compounds. A thermal imager will search for unusually warm regions. The Reason radar instrument will transmit waves into the ice to investigate its structure and thickness. Dust and mass analyzers will examine material in the space near Europa. The gravity experiment will track how the moon deforms, while the magnetometer works with the plasma instrument to distinguish Europa's internal induction response from distortions created by charged particles outside. Europa Clipper's magnetometer is not SICMAG or OPUS Magnum. The mission uses 3 fluxgate sensors mounted on a long boom, relying on a magnetometer technology with a long history of use in space. The solid-state quantum sensors being developed at JPL belong to a different technological path and may serve later missions if they achieve the necessary sensitivity, stability, and flight readiness. This distinction is important. Europa Clipper is not evidence that the new quantum magnetometers have completed development. Instead, the spacecraft shows that current technology can perform excellent science through large, carefully tested systems with many layers of support. SICMAG and OPUSMAGNM ask a different question: whether some of that capability might eventually be placed into instruments that are smaller, lighter, and easier to distribute across multiple platforms. When Europa Clipper arrives, its magnetometer will not work alone. The plasma environment around Europa can distort the magnetic field and create effects that may be confused with the ocean's response. The PIMS instrument will measure charged particles to help separate plasma effects from the induced field, carrying information about the moon's interior. Radar and gravity measurements will add further constraints on ice thickness and internal layering. It is this combination of observations that may narrow the range of possible ocean models. A future quantum magnetometer would also need to operate within a similar system. Greater sensitivity would not make the other instruments unnecessary. It would simply provide a better magnetic measurement or make that measurement possible within a smaller package. To turn the signal into an understanding of the ocean, scientists would still need to know the state of the plasma, the spacecraft's position, the characteristics of the background field, and the structure of the ice. More distant worlds would require this kind of coordination even more. A spacecraft traveling to Uranus could study the planet's magnetic field, its rings, its plasma environment, and moons that show signs of geological activity. A mission to Neptune could examine the planet's magnetic field, its interaction with the solar wind, and its distant system of moons. In both cases, a small magnetometer that uses little power and can monitor its own drift would free up resources for other instruments. Measurements could also continue for much longer periods. Instead of switching the sensor on only when the spacecraft approaches its target, a low-power magnetometer could monitor the environment through most of the journey. It could measure the solar wind between planets, record magnetic variations as the spacecraft moves through different regions, and create a continuous line of data connecting Earth to the destination world. Data collected during the journey would not be merely secondary. The solar wind carries the sun's magnetic field throughout the solar system. By measuring it at great distances, scientists can study how magnetic structures change and interact as they travel. A spacecraft moving toward a distant planet is not only carrying instruments to a destination, it can also become an observing station in a region of space that is rarely measured directly. Once it arrives, the sensor takes on another role. It monitors the planet's magnetosphere, records waves, and plasma currents, measures the responses of moons, and compares the field at different altitudes. A single small instrument can collect several layers of information throughout the life of the mission. This is the vision that makes miniaturization meaningful. The goal is not simply to build a smaller magnetometer for the sake of saying it is small. Its value lies in the kinds of missions that a compact sensor may enable. More sensors aboard one spacecraft, more spacecraft within a system, longer journeys with less power, and measurements sustained for years without complex recalibration. Even so, every advantage comes with a condition. The device is useful only if its sensitivity is high enough. Radiation resistance matters only if the complete electronics and readout system can withstand radiation as well. Self-calibration is meaningful only after it has been tested through repeated thermal cycles and long periods of operation. Calling a sensor quantum does not automatically free it from the engineering problems of spacecraft. For that reason, development proceeds in small steps. Sensitivity is measured inside shielded chambers. Devices are heated and cooled. Materials are exposed to radiation. Readout circuits are miniaturized. Models of spacecraft interference are incorporated into testing. Each step answers one part of the question of whether the technology is ready to leave the laboratory. In a future mission, a solid-state quantum magnetometer may travel aboard a small spacecraft passing an icy moon. Several sensors may be distributed around the spacecraft to remove its own magnetic interference. The technology may also be used first to measure planetary magnetic fields or the solar wind, where the scientific requirements differ from those of searching for an ocean. The exact path has not yet been decided because the instruments are still under development and the missions that might use them remain in the future. Wherever it is used, a magnetometer still measures only one quantity: the magnetic field at the sensor's location. The meaning of that measurement depends on the question being asked. Around a planet, it may provide information about the core and magnetosphere. In the solar wind, it tracks magnetic structures moving through space. Near an icy moon, it may detect the response of a conductive liquid layer hidden deep inside. That signal may indicate that an ocean probably exists and, when combined with other measurements, may help estimate its conductivity, depth, or thickness. It does not directly reveal whether the water is clear or cloudy, warm or cold at any particular location. It cannot photograph the seafloor or detect an organism moving through the darkness. Even a perfect magnetic measurement could not prove on its own that life exists. Salt water conducts electricity whether it contains organisms or is completely sterile. The ions still respond to the magnetic field, currents still form, and the secondary magnetic field still passes through the ice. The sensor records only that physical response. Assessing the possibility of life requires different questions. Does the ocean contain the necessary elements? Does the water interact with rock in ways that can produce useful chemical reactions? Is there an energy source that persists long enough? Can material from the surface be transported downward? Has the environment remained stable over geological time? Answering those questions requires data from many kinds of instruments and may ultimately require direct analysis of material from the ocean. A magnetometer is therefore not a life detection machine. It is a tool for identifying where an important environment may exist. It helps reveal which doors deserve closer investigation, which worlds may contain conductive liquid layers, and how their interiors respond to their parent planets. Europa Clipper is carrying many instruments toward one such door. SICMAG and Opus Magnum represent efforts to make future keys smaller, lighter, and more durable. On one side is a large spacecraft already making a real journey. On the other are crystals and circuits still being tested in laboratories. They occupy different stages of development, but both are directed toward understanding worlds whose surfaces do not reveal everything hidden inside. In the future, a quantum sensor may leave its magnetically shielded chamber, survive many years in space, and enter the environment of a distant planet, It would measure magnetic fields no human eye could ever see and identify a slight distortion among plasma, radiation, and interference from the spacecraft itself. From that distortion, models might reveal a conductive liquid layer beneath the ice. That would be a major achievement, but it would still be only the beginning of a larger question. Detecting an ocean tells us where water may exist. It does not reveal what that ocean may have produced, how far its chemistry has progressed, or whether the darkness beneath the ice is completely empty. A precise magnetic field measurement can reveal the structure of a world. It cannot tell the entire story of that world by itself. On the surface of Europa, almost nothing seems to change. The ice stretches all the way to the horizon, cold, rigid, and divided by reddish-brown markings that have endured for spans of time longer than all of human history. No open water lies exposed beneath the faint sunlight. There is no sound of waves, no shoreline, and no obvious sign that beneath this frozen shell there may be an ocean larger than all of Earth's oceans combined. Jupiter still hangs above, filling a vast portion of Europa's sky. Bands of cloud continue to curl through the planet's atmosphere, while its immense magnetic field reaches far into space, surrounding the moon's orbit. Jupiter rotates rapidly, and with that rotation, the magnetic environment at Europa continually changes. This process did not begin when humans first observed the moon, nor did it wait for a spacecraft to pass nearby. It has continued for billions of years, steady and almost entirely invisible. The magnetic field enters the ice without leaving a new fracture behind. It does not make the surface glow or produce a sound that can travel through the emptiness. Far below, where sunlight has never reached, the salty ocean responds. Ions dissolved in the water shift by a very small amount, not in the form of great waves, but as weak electrical currents spreading through the enormous body of water. Those currents generate a magnetic field of their own. The secondary field is far weaker than Jupiter's, but it still exists. It travels back outward, passing through the ice, merging with the surrounding magnetic environment, and slightly altering the overall shape of the field around Europa. A field line bends by a small amount. A new component appears in the signal. A measured value differs from what models would predict if the interior contained only ice and rock. No creature on the surface could sense that change directly. Humans cannot see it either. A magnetic field has no color, creates no clear outline against the sky, and leaves no image like sunlight reflected from ice. But a spacecraft passing nearby can carry an instrument sensitive enough to recognize that the space around the moon has been. The sensor does not see the ocean. It records only the strength and direction of the magnetic field at each moment. Those numbers are compared with the spacecraft's position, Jupiter's rotation, and the state of the surrounding plasma environment. Once the known influences are taken into account, what remains may carry the trace of a conductive liquid layer hidden far below. On Earth, another story unfolds inside an almost perfect crystal. Carbon atoms, or silicon and carbon atoms, arrange themselves in repeating patterns, forming a strong and stable structure. But at one site, an atom is missing. Somewhere else, another atom occupies the wrong position. These extremely small irregularities give the surrounding electrons unusual quantum states. In many materials, a defect like this would simply be treated as something to reduce or remove. Here, however, that imperfection becomes the most valuable part. It creates a place where light can prepare an electronic state. Electrical or microwave signals can influence the spin, and an external magnetic field can alter the spacing between energy levels. The change is extremely small. It does not make the crystal vibrate in a way a person could feel, nor does the emitted light necessarily change color in any obvious way. An optical detector or electronic circuit must follow subtle differences, repeat the measurement many times, and separate the spin response from temperature changes, electronic noise, and other influences. From such a measurement, a number appears. Many numbers form a sequence of data. That sequence is compared with models of magnetic fields, oceans, and the moon's internal structure. Gradually, Something that has never been seen directly begins to take shape within science. There is no mysterious leap between Europa's hidden ocean and the defect inside the crystal. There is only a very long but continuous chain of interactions. Jupiter's magnetic field changes. The salty water responds. Ions form electrical currents. Those currents create a secondary magnetic field. That field reaches the spacecraft. Electron spins inside the crystal react. Light or electric current carries the information outward for humans to read. In a sense, each step becomes smaller than the one before it. A giant planet influences a moon. The moon contains an ocean beneath its ice. The ocean distorts an invisible field. That field changes the states of electrons surrounding an atomic-scale defect. In the end, an extremely faint signal passes through an electronic system and becomes data on Earth. There is a quiet symmetry in the entire process. One of the largest structures that may be hidden inside Europa is detected through one of the smallest structures humanity can control. The ocean may be tens of kilometers deep, while the color center in the crystal exists around only a few atomic sites. One end approaches the scale of a planet, while the other lies within the quantum world. Even so, the technology does not make the ocean any less mysterious. A magnetic signal may reveal a conductive liquid layer, but it cannot directly describe what is happening within the water. It does not show how currents move through the ocean, what the seafloor looks like, or which chemical reactions are unfolding in the darkness. Still less can it answer on its own whether life has ever appeared there. Those questions remain ahead. They will require radar, gravity measurements, compositional analysis, thermal data, and perhaps one day an instrument that truly descends beneath the ice. A magnetometer opens only one way of listening, a method for recognizing that the interior of a world is responding to the environment outside. Perhaps that is also what makes Europa so extraordinary. The moon does not need to reveal its ocean at the surface. It only needs to continue moving around Jupiter. The magnetic field keeps sweeping past. The salty water keeps responding. The signal continues to form, whether or not a spacecraft is there to measure it. For a very long time, no instrument listened to that response. Magnetic field lines passed inward and outward again, carrying traces of the ocean through the ice without anyone knowing. Only when humanity learned to measure extremely small changes did this familiar signal of nature begin to become information. The quantum sensors now under development still have a long journey ahead before they can perform this work on a real mission. They must become smaller, more stable, and durable enough to survive many years in space. One design may prove suitable for a large spacecraft. Another may eventually fly aboard a smaller vehicle. The exact path has not yet been decided, but the underlying idea has already revealed a remarkable possibility. An empty site within a crystal can become sensitive to a magnetic field. An imperfection in an atomic lattice can act like a compass without a needle, and that compass may help humanity detect an ocean that has never been seen. On Europa, the ice still conceals the deepest part of the moon. Jupiter continues to turn. The ocean remains in darkness. Its ions still move to the rhythm of an invisible field, producing a response so faint that only the most precise instruments may be able to recognize it. Some oceans lie too deep for light to reach. Some signals are too small for human senses to detect. Yet between the unimaginably large and the unimaginably small, a bridge still exists, formed from salty water, electric currents, magnetic fields, and quantum spin. An ocean can bend a magnetic field line ever so slightly. A defect within a crystal can detect that change. And from a variation that is almost impossible to notice, the shape of a world never directly seen begins to emerge.